Incredibly, America's enemies have tried to attack Marine One over 47 times in the past decade, but failed each time. This $80 million chopper rises from the White House lawn with missile jammers, decoys, and bulletproof windows, making it a fortress in the sky. It can even coordinate nuclear response while flying through storms. Yet experts wonder, could it withstand an electromagnetic pulse attack? And why are Pentagon officials so secretive about its ghost mode radar invisibility? Join us as we explore the $80 million presidential helicopter, the MV-22 Marine One. Few people know that America's prestigious presidential helicopter fleet started because of atomic bombs. In 1946, while watching nuclear tests at Bikini Atoll, Marine General Roy S. Geiger had a startling realization. Traditional beach landings were becoming too dangerous in the atomic age. With troops, ships, and equipment clustered together on beaches, they'd be perfect targets for nuclear weapons. This concerning observation led to the birth of Marine Helicopter Squadron 1, also known as HMX-1, on December 1, 1947. Under the command of Colonel Edward C. Dyer, this experimental unit set up shop at Marine Corps Air Station, Quantico, Virginia. The location wasn't random. It was strategically chosen to be near both the Sikorsky and Piasecki helicopter plants in Connecticut and the Marine Corps schools, where they would find their first pilots and crew members. The squadron started with two helicopter models, the nimble Sikorsky HO-3S1 and the larger Piasecki HRP-1, nicknamed the Flying Banana because of its unusual curved shape. These early helicopters were primitive by today's standards, as they lacked basics like cabin heating and could only carry 3 Marines at a time. In May 1947, HMX-1 conducted its first major test. 5 helicopters launched from the deck of the USS Palau, an aircraft carrier, and transported 66 Marines to Camp Lejeune, North Carolina. While it took multiple trips due to the small passenger capacity, this test proved that helicopter transport was not just possible, it was the future of military mobility. The Marine Corps quickly recognized the potential of these flying machines. In 1948, they published their first manual for helicopter operations, officially titled Amphibious Operations, Employment of Helicopters, or FIB 31. The Marines coined the term vertical envelopment instead of the more commonly used air mobility, or air assault, emphasizing their unique approach to aerial combat tactics. When the Korean War broke out in 1950, HMX-1 faced its first real combat test. 4 of its helicopters joined the VMO-6 squadron to support the 1st Provisional Marine Brigade during the crucial Battle of Pusan Perimeter. These helicopters proved invaluable for battlefield observation, controlling troop movements, evacuating wounded soldiers, and rescuing downed pilots. During the brutal Chosin Reservoir campaign, HMX-1 helicopters served as vital communication links between Marine units spread along the reservoir's western edge. The squadron's success in Korea was so impressive that it was tasked with training new helicopter pilots to meet the growing demands of the war. Many of these pilots would go on to form HMR-161, the Marine Corps' first dedicated helicopter transport squadron. Today's Marine One fleet, with its advanced technology and prestigious mission, traces its roots back to those pioneering days of military helicopter aviation. The squadron's early focus on safety, precision, and reliability, developed during those first experimental flights and combat missions, remains evident in every presidential flight they conduct today. After proving itself in military operations, could anyone have predicted that HMX-1's next mission would involve transporting the most powerful person in the world? The transformation began on September 7, 1957, during what seemed like a routine day. President Dwight D. Eisenhower was vacationing in Newport, Rhode Island, when urgent news arrived about the Little Rock 9 crisis. 9 black students were being blocked from attending Central High School by the Arkansas National Guard, creating a constitutional crisis that demanded the president's immediate attention. The traditional return route to Washington was painfully slow. An hour-long ferry ride, followed by a 45-minute flight on Air Force One, and topped off with a 20-minute motorcade to the White House. With time critical, someone remembered that there was an HMX-1 UH-34 helicopter standing by on Aquaneck Island for emergencies. Colonel Virgil D. Olson, who would become a legendary figure in Marine One history, received the urgent call. Within minutes, he and his crew rushed to the Naval War College, where the Eisenhowers were staying. The historic 6-minute flight across Narragansett Bay to Air Force One changed presidential travel forever. Colonel Olson didn't just fly the first presidential helicopter mission, he revolutionized the entire operation. He introduced several innovations that are still used today, including the distinctive white-top paint scheme that gave these helicopters their famous white-top nickname. When the White House gardener complained about rotor wash destroying the South Lawn's landscaping, Olson created the iconic white circular landing target that Marine One still uses today. The presidential helicopter fleet evolved through several aircraft generations. The VH-34 Choctaw served as the first official presidential helicopter in 1957, followed by the VH-3A Sea King in 1962. The VH-3D Sea King, introduced in the late 1970s, brought significant improvements in comfort and security. In 1987, the smaller, more agile VH-60N White Hawk joined the fleet, offering better performance for overseas missions. What many people don't know is that until 1976, the Army shared presidential helicopter duties with the Marines, using the call sign Army One when carrying the president. The Marines' exceptional service record led President Gerald Ford to assign them sole responsibility for presidential helicopter transport. A historic milestone occurred on July 16, 2009, when Major Jennifer Greaves commanded the first all-female Marine One crew. This groundbreaking flight, which was also Greaves' final mission as the first female presidential helicopter pilot, demonstrated how far the squadron had come from its all-male beginnings. The presidential helicopters have witnessed countless historic moments. They evacuated President Richard Nixon from the White House after his resignation, transported presidents to secret bunkers during national emergencies, and even helped Ronald Reagan bypass Washington traffic to visit his wife Nancy in the hospital. Modern Marine One helicopters are technological marvels compared to their predecessors. They feature advanced communication systems that allow the president to run the country from the air, defensive countermeasures that can defeat missiles, and secure video conferencing capabilities. The cabins are designed to provide the same level of comfort and functionality as the Oval Office, ensuring the president never loses a moment of productivity. Looking ahead, the Marine One fleet continues to evolve. The new VH-22A Patriot, which made its first presidential flight in 2024, represents the next chapter in this prestigious legacy. With enhanced range, speed, and security features, these aircraft ensure that the president can respond to any crisis, anywhere in the world, at a moment's notice. But perhaps the most remarkable aspect of Marine One's evolution isn't the technology, it's the unwavering dedication to excellence that began with Colonel Olson's historic flight and continues with every Marine One mission today. While Marine One's legacy of excellence has never wavered, what happens when even the most prestigious helicopter fleet in the world faces the harsh reality of aging aircraft and changing threats? The quest to modernize Marine One began in the early 2000s, sparked by a sobering realization after the September 11 attacks. The existing helicopters, though reliable, couldn't accommodate the new security equipment and communication systems needed for an increasingly dangerous world. They had become so loaded down with added gear that their performance was suffering. In 2005, the Pentagon launched what seemed like a straightforward plan: replace the aging fleet with the VH-71 Kestrel, a modified version of a European helicopter called the Augusta-Westland AW101. The initial budget was $6.1 billion for 28 helicopters. However, this project soon became a cautionary tale in military procurement. As requirements grew, costs skyrocketed. Each helicopter's price tag ballooned to $400 million, which was more than Air Force One, the president's customized 747 jumbo jet. The program's total cost eventually reached a staggering $13 billion, leading to its cancellation in 2009. This left the Marine Corps in a difficult position, forced to keep maintaining their aging fleet while searching for a new solution. During this period, Marines had to become increasingly creative in maintaining the existing helicopters. They established partnerships with museums housing retired presidential helicopters to salvage spare parts that were no longer manufactured. Engineers developed innovative ways to manufacture replacement components using 3D printing technology, a practice that was revolutionary at the time. The failure of the VH-71 program led to a complete overhaul in how the military approaches presidential helicopter procurement. Instead of trying to create an entirely new aircraft, they decided to modify an existing proven design. This led to the selection of Sikorsky's S-92 helicopter, which would become the VH-92A Patriot. The VH-92A program has been remarkably different from its predecessor. By building on a helicopter already in commercial service, developers could focus on presidential-specific modifications rather than solving basic aircraft design challenges. The contract, awarded in 2014, called for 21 helicopters at a significantly lower cost per aircraft. The new helicopter brings impressive capabilities to the White House fleet. Its cabin is 30% larger than the previous Marine One, allowing for more security personnel and equipment. Advanced fly-by-wire controls make it easier to pilot in challenging conditions. Perhaps most importantly, its modular design allows for easier upgrades as technology advances. One fascinating aspect rarely discussed is the extensive testing these helicopters undergo. Before carrying the president, each VH-92A must complete a series of unusual trials. These include landing in artificial sandstorms, flying through simulated electromagnetic pulses, and even surviving simulated lightning strikes. The helicopters must also prove they can safely land on the White House lawn without damaging the historic gardens, a requirement that dates back to Colonel Olson's day. The VH-92A made its first operational presidential flight in August 2024, marking the beginning of a new era for Marine One. The remaining fleet is scheduled to be fully operational by 2025, gradually replacing the trusted VH-3D and VH-60N helicopters that have served presidents for decades. This modernization effort represents more than just new helicopters. It's a complete reimagining of presidential transport for the modern age. With threats ranging from cyber attacks to electromagnetic warfare, these aircraft must serve as both transport and mobile command centers, ready for any crisis that might emerge. With cutting-edge helicopters ready to serve, how does Marine One stay one step ahead of ever-evolving security threats in today's complex world? The answer lies in what insiders call the presidential shell game, a carefully choreographed dance of identical helicopters that keeps adversaries guessing. When Marine One takes off, it's never alone. Up to 5 identical helicopters fly in formation, constantly shifting positions to hide which one carries the president. This aerial ballet is so effective that even sophisticated surveillance systems can't reliably track the presidential aircraft. What makes these helicopters instantly recognizable is their distinctive white top appearance. Dark green bodies crowned with pristine white paint above the windows. But this isn't just for looks. The color scheme, originated by Colonel Olson in the 1950s, helps reduce solar heating in the cabin and makes the aircraft easily identifiable to authorized personnel. Behind these missions stands an elite force of over 800 Marines, each holding the highly restricted Yankee White security clearance. This clearance is so stringent that even a distant relative's questionable activities can disqualify a candidate. Every Marine must pass extensive background checks, regular polygraph tests, and continuous security monitoring. The squadron operates from 3 main locations: Marine Corps Air Facility Quantico, which is their headquarters, Joint Base Anacostia Bowling in Washington, D.C., and Joint Base Andrews in Maryland. What's less known is that each facility maintains hardened shelters with their own power supplies, enabling operations even during widespread emergencies. Marine One's defensive capabilities remain largely classified, but some details have emerged. The helicopters carry advanced electronic warfare systems that can jam enemy radar and missile guidance systems. Special infrared countermeasures can confuse heat-seeking missiles, while chaff dispensers release clouds of metal strips to deflect radar-guided threats. The security extends to maintenance procedures. Every part installed on Marine One must have a documented chain of custody from manufacture to installation. Tools are carefully inventoried, and work areas are swept for electronic devices. Even the fuel undergoes special testing before each flight, a practice implemented after a 1970s incident when contaminated fuel almost caused a presidential helicopter emergency, transportation of Marine One itself involves another layer of security. When the president travels, the helicopters are airlifted by Air Force C-17, Globemaster III, or C-5 Galaxy transport planes. These massive aircraft carry not just the helicopters, but also spare parts, maintenance equipment, and support personnel. The loading process happens inside secure hangars, shielded from prying eyes. One lesser-known aspect of Marine One operations is the extensive weather monitoring system. A network of automated weather stations around Washington, D.C. provides real-time data to crews. This system can detect dangerous wind conditions around the White House and other landing zones, crucial for safe operations in urban areas. Communication is another critical component. Marine One maintains simultaneous connections with multiple military and civilian networks, ensuring the president never loses contact with military commanders or emergency services. The helicopter can receive secure data from satellites, ground stations, and other aircraft, creating a comprehensive picture of potential threats. The Marines constantly train for worst-case scenarios. In secure facilities, they practice responding to everything from mechanical failures to electromagnetic pulse attacks. These drills often involve multiple agencies and take place in simulators so advanced they can replicate the feel of landing on the White House lawn during a storm. Despite all these security measures, perhaps the most remarkable fact about Marine One is its perfect safety record. No presidential helicopter has ever been involved in an accident or successful attack. This testament to Marine Corps dedication raises an intriguing question. As technology continues to advance at breakneck speed, what new security innovations will protect future presidents in the skies above Washington? The Bell Boeing 522. Osprey is a unique aircraft that combines the capabilities of a helicopter and an airplane. Known as a tilt-rotor aircraft, it takes off and lands vertically like a helicopter, but can fly at high speeds and cover long distances like a fixed-wing airplane. The Osprey was designed to meet the United States military's need for a versatile, high-speed transport vehicle, especially after challenges encountered during the Iran hostage crisis in 1980. Its innovative design allows it to carry troops and cargo over long distances and difficult terrains quickly, making it an essential tool in modern military operations. The V-22 Osprey's ability to switch between helicopter and airplane modes is due to its tilt-rotor technology. This feature allows the rotors at the end of each wing to rotate. When the rotors face upwards, the Osprey can take off and land vertically. Once airborne, the rotors rotate forward, enabling it to fly like an airplane at speeds and ranges far beyond what most helicopters can achieve. In airplane mode, the Osprey reaches speeds of up to 316 miles per hour, and its maximum range exceeds 1,000 miles, making it a highly efficient choice for long-distance missions. Initially developed in the 1980s, the Osprey took over 20 years to refine and field test before becoming operational in the United States Marine Corps in 2007. The United States Air Force followed in 2009 with its version, the CV-22B, designed specifically for long-range missions. The United States Navy joined in 2021 with the CMV-22B model adapted for aircraft carrier missions. The Osprey's versatility has made it a valuable asset across different branches of the United States military, and even the Japanese self-defense forces use the aircraft. One of the most notable uses of the Osprey is its role in transporting personnel for presidential support missions. For such critical tasks, reliability, speed, and versatility are crucial. The Osprey can transport security teams, equipment, and staff to remote locations efficiently, and its ability to land in confined spaces adds to its value in these missions. In terms of technical specifications, the V-22 is powered by two Rolls-Royce AE1107C engines, which allow it to continue flying even if one engine fails. Its advanced avionics include a glass cockpit, a digital interface with multiple screens that display maps, navigation, and system status. The Osprey's flight control system is triple redundant, meaning it has multiple backups to ensure safe operation. And it has damage control features that can automatically adjust to isolate damaged areas. To help the Osprey handle a range of operations, its design includes both composite materials for durability and foldable rotors for compact storage, especially useful for shipboard operations. One challenge for the Osprey is the heat from its powerful engines, which can potentially damage the decks of ships. To address this, the Navy uses portable heat shields and has tested heat-resistant coatings on ships. These modifications ensure that the Osprey can operate safely on various naval platforms without causing excessive wear and tear on the decks. In terms of defense, the Osprey can be equipped with a machine gun on its rear ramp, providing basic self-defense during missions. Although originally explored as an option, more sophisticated weapon systems have not been broadly implemented due to the aircraft's high speed, which allows it to avoid many threats. Since entering service, the V-22 Osprey has been used in several high-profile operations, providing rapid transport for troops, medical evacuations, and supplies in conflict zones like Iraq, Afghanistan, and Libya. Its ability to take off and land almost anywhere, combined with its speed and range, has redefined military logistics and expanded possibilities for future missions. Could this tiltrotor technology be a glimpse into the future of military aviation? Over the years, numerous military arsenals have emerged, but few remain as significant as the United States bunker buster weapon. Recently, the deployment of the 30,000-pound bunker buster in Yemen has drawn global attention, and its impressive penetrating power, regardless of advanced reinforcements of any surface, has further increased the intrigue surrounding it. What specific outcomes were observed in Yemen? And does this weapon truly represent a transformative advancement in military technology? Join us as we explore the capabilities of the United States 30,000-pound bunker buster. Recently, the United States Air Force conducted successful tests of the GBU-72/B, a powerful 5,000-pound bunker buster bomb. These tests included dropping a prototype from an F-15E Strike Eagle over a range linked to Eglin Air Force Base in Florida. The development of this bomb falls under a program known as the Advanced 5,000-Pound Warhead. But before we delve into the details of this 5,000-pound bunker buster bomb, let's decide just how much of a game-changer and what the impact of the United States 30,000-pound bunker on Yemen will be. These advanced munitions, known as bunker busters, are weapons created particularly to penetrate great depths before delivering devastating explosive force. In modern warfare, critical targets are sometimes hidden in almost impenetrable underground subterranean facilities. These facilities are impenetrable because they are protected with advanced reinforcements that are resistant to conventional aerial bombardment. These facilities are what the bunker busters are built to penetrate. The exceptional effectiveness of bunker busters can be linked to two primary design features. First, their specialized warheads, which are found inside reinforced shells, can pass through multiple layers of protective material while retaining structural integrity. This ensures that the munition reaches its target before detonation. Second, their delayed fuses are programmed to trigger the explosive payload only after achieving the desired depth, thereby maximizing the internal destruction of the target. The development of these munitions can be traced back to the Second World War. During this period, British engineer Barnes Wallis designed the Tall Boy and Grand Slam bombs, which demonstrated remarkable destructive power by demolishing heavily fortified Nazi infrastructure. These early designs laid the foundation for future advancements in penetration technology. The Cold War era further accelerated the refinement of such weapons, driven by the escalating need to counter increasingly secure adversarial facilities. Moving on to the 21st century, bunker busters became indispensable in conflicts such as the Gulf War and the campaigns in Afghanistan. One major example is the GBU-28, a 5,000-pound precision munition capable of penetrating 20 feet of reinforced concrete or 100 feet of compacted earth before detonation. The successful deployment during the Gulf War against fortified Iraqi bunkers showed its importance. What led to the development of these extremely essential weapons of warfare? Major advancements in this field began with the development of the GBU-57 Massive Ordnance Penetrator, a munition weighing an extraordinary 30,000 pounds. This weapon is engineered to penetrate up to 200 feet of reinforced concrete, specifically targeting deeply buried facilities such as nuclear installations. Often referred to as the father of all bombs, the GBU-57 possesses 4 times the destructive power of its predecessor and stands as the most potent non-nuclear weapon ever developed. This bunker buster, also known as the Massive Ordnance Penetrator, is a powerful symbol of modern military dominance. Its creation demanded not only cutting-edge technology, but also a financial investment, estimated at 400 to 500 million, enough to build a fleet of small warships. Each GBU-57 costs about $3.5 million to produce, starkly contrasting the $26,000 price tag of the much smaller GBU-2000 laser-guided bomb. This massive difference highlights the sheer sophistication, destructive power, and strategic value of the GBU-57. In May 2023, the U.S. military made headlines by releasing striking images of the GBU-57 on the official Facebook page of Whiteman Air Force Base in Missouri. These images quickly went viral, but they served a deeper purpose, a subtle warning. Whiteman Air Force Base is home to the B-2 Spirit, the only stealth aircraft capable of deploying this colossal bomb. The pairing of the GBU-57 and the B-2 Spirit creates a fearsome combination. Imagine a stealth bomber slipping past radar defenses to drop a bomb powerful enough to obliterate fortified underground targets. Few defenses could withstand this devastating duo. Meanwhile, the GBU-31J Dam showcases a different kind of precision and strength. Weighing about 2,000 pounds, it combines advanced GPS-guided technology with a warhead capable of piercing concrete, steel, or rock before detonating. Its intelligent guidance system ensures pinpoint accuracy with minimal collateral damage, making it an ideal weapon for strategic strikes. First used in combat during Operation Allied Force, J-Dams paired with B-2 bombers demonstrated unmatched precision and endurance. Missions lasted up to 30 hours, and over 600 bombs were deployed. No weapon can match the deadly mix of unmatched stealth and pinpoint accuracy. But this is just the start. The J-Dam family keeps evolving. The Mk-82, a 500-pound bomb, emerged in 1999 as a chilling warning of the future. With enhanced GPS precision, cutting-edge navigation sensors, real-time target updates, and devastating new warheads, these advancements turn each step into a nerve-wracking leap forward. From Iraq to Afghanistan, the GBU-31 has demolished underground bunkers and key facilities, proving its unstoppable power when deployed by legendary aircraft like the B-52 or F/A-18. Meanwhile, the Taurus KPD-350, a joint creation of Germany and Sweden, has redefined destruction. This missile can punch through 26 feet of reinforced concrete, leaving even engineers in awe. With a range of over 310 miles, it strikes from far beyond enemy defenses, delivering devastation with its tandem warhead. Armed on Eurofighter Typhoons or Gripens, it can single-handedly dismantle an entire defense system. In May 2023, the UK's decision to send Storm Shadow missiles to Ukraine sparked fresh tensions, and Germany faces mounting pressure to supply the Taurus, a weapon with the power to alter the course of conflicts. South Korea recently purchased Taurus missiles for $18 million, signaling a clear warning to North Korea. The missile's ability to destroy targets before detection makes it a game-changer. However, the AGM-158 JASSM stands as a stealthy phantom of modern warfare. With its sleek design, silent flight, and a 1,000-pound warhead, it bypasses defenses undetected. Variants like the AGM-158C add anti-ship capabilities, boasting a range of up to 575 miles. The latest JASSM XR stretches this range to 1,240 miles, making distance irrelevant and leaving adversaries defenseless. The B-2 Spirit, an icon of U.S. air power, takes these weapons to new heights. Known as the ultimate stealth bomber, it's invisible to radar, can carry up to 66,000 pounds of weapons, and fly over 6,800 miles without refueling. Its design ensures it can strike any target, anywhere, while remaining undetected. The B-2 is both a marvel and a financial giant at $2 billion per unit, outclassing most defense investments. As technology advances, these weapons and platforms mark a new era where no place on Earth feels truly safe. However, keeping it in top condition is no small feat. According to the Los Angeles Times, the aircraft undergoes a major overhaul every 7 years, costing $60 million and taking an entire year to complete. Each hour it spends in the sky requires 50 to 60 hours of maintenance on the ground. This raises the question, is its hefty price tag worth it? The answer lies in its extraordinary capabilities. Combining stealth, long range, and a massive payload, the B-2 is designed to cripple enemy defenses and deliver devastating blows, even against heavily fortified targets. Its precision-guided bunker-busting bombs, such as the GBU-57 MOAB, can destroy deeply buried structures, proving that no hideout is truly secure. These weapons are not just advanced tools. They showcase human ingenuity in overcoming the toughest challenges on the battlefield. Beyond aircraft, robots like Bear or Battlefield Extraction Assist Robot are transforming combat zones. Designed to rescue injured soldiers, Bear can lift up to 595 pounds and carry out various tasks, from breaking into vehicles to transporting supplies. Equipped with cameras, sensors, and artificial intelligence, it navigates obstacles and follows commands with remarkable precision, making it an invaluable asset on the battlefield. Another standout is the Vision 60 robot by Ghost Robotics, built for rugged terrains and extreme environments. With a 360-degree camera, it excels in surveillance, reconnaissance, and supply transport. Whether on land or underwater, its versatility and efficiency make it a critical tool in military operations. Finally, innovations like GuardBot, a spherical surveillance drone, expand the possibilities of modern warfare. Capable of navigating both land and water, it can detect hazardous materials and unexploded ordnance, reducing risk for human teams and enhancing battlefield safety. As military technology continues to advance, tools like stealth bombers and combat robots redefine how wars are fought. These machines are not just weapons, they're game changers in strategy and survival. What are your thoughts? Would anyone trust robots or stealth bombers to handle high-stakes missions? The Guardian XO is an advanced exoskeleton designed by Sarcos Robotics to assist humans in heavy lifting and mobility tasks. This innovative device can lift and carry up to 200 pounds with ease, significantly reducing strain on the user. Despite weighing approximately 150 pounds, the exoskeleton is equipped with a hot-swappable battery system, allowing continuous operation for up to 8 hours. Its design prioritizes agility and functionality, enabling users to move naturally, walk, bend, or turn at speeds of up to 3 miles per hour. The Guardian XO incorporates intelligent sensors and AI-driven dynamics, ensuring it responds smoothly and precisely to user movements. It distributes force evenly and maintains balance on uneven or rough terrain, with automatic balance adjustments to enhance safety during use. Its simple activation process and short learning curve make it an excellent tool for logistics, transportation, and military operations requiring precision and strength. For soldiers, this exoskeleton is a revolutionary tool. By taking on the physical burden of carrying heavy equipment, it allows them to conserve their energy and focus on critical tasks. The U.S. military has shown significant interest in deploying the Guardian XO, viewing it as a key component of future combat strategies. This technology marks a shift in warfare, where robots, drones, and exoskeletons work alongside humans to enhance safety and efficiency. Similarly, Boston Dynamics has developed the Big Dog robot, a machine designed for challenging terrains. Weighing 240 pounds, this robust robot can transport loads of up to 750 pounds across snow, hills, and deserts at speeds of 4 miles per hour. It is an engineering achievement that complements human efforts in harsh environments. As we look toward a future where robotics and exoskeletons play a central role in various fields, these technologies offer exciting possibilities. They are not intended to replace humans, but to work in partnership with them, extending physical capabilities and improving performance in demanding conditions. Big Dog operates using a powerful 50-horsepower, 4-stroke gasoline engine combined with an advanced hydraulic drive system. This combination allows it to overcome large obstacles and navigate uneven terrains such as rocks, mud, and rough ground. The robot is equipped with over 50 intelligent sensors, including accelerometers, force sensors, motor speed sensors, temperature sensors, and hydraulic pressure sensors. These sensors transmit data to its integrated computer system, enabling Big Dog to automatically adjust its movements to maintain stability and ensure safety, even while carrying heavy loads. Big Dog's advanced stabilization system ensures excellent balance on challenging terrain or when encountering unexpected obstacles. With a full fuel tank, it can operate continuously for 1 hour, providing vital support in emergencies. Whether transporting military supplies or essential combat equipment, Big Dog significantly reduces the burden on soldiers. In the future, it is expected to take on even more critical roles, moving across rough terrain, carrying heavy loads, and operating flexibly. This makes it a potential life-saving companion for dangerous missions, enhancing combat effectiveness and potentially replacing soldiers in high-risk tasks. Similarly, Eagle Prime, developed by Megabots, represents a remarkable advancement in combat robotics. Initially introduced as an entertainment project for robot battles, this 12-ton, 16-foot-tall giant robot soon caught the attention of the U.S. military for its potential applications. Powered by a 6.2 LV8 gasoline engine, producing 430 horsepower, Eagle Prime combines impressive size and power with surprising agility, capable of launching powerful attacks on the battlefield. The robot is equipped with a large cannon and a grappling hook, allowing it to handle close combat missions or provide tactical support. Its cockpit accommodates 2 operators, one controlling its movements and the other managing its weapons, optimizing performance in complex scenarios. Additionally, Eagle Prime includes remote control functionality, enabling it to operate safely in hazardous environments without endangering human operators. With a development cost of $2.3 million, Eagle Prime is not only a combat machine, but also a symbol of the potential for advanced robotics. While it currently supports combat missions and can reduce risks for soldiers in dangerous situations, fully replacing humans in military operations remains a challenge. Despite its remarkable capabilities, systems like Eagle Prime primarily serve as support rather than standalone combat units. This raises an important question. Will robots like Eagle Prime remain as allies to soldiers, or will they eventually become key players on the battlefield? Another one is the FLIR Cobra robot system, developed by Endeavor Robotics, is one of the most versatile robotic systems employed by the U.S. military. With its robust design and advanced capabilities, it serves as a key tool in critical missions. Let's take a closer look at its impressive features. Powered by a durable engine, the FLIR Cobra weighs 366 pounds and can reach a top speed of 8 miles per hour. It is capable of operating continuously for up to 10 hours, supporting essential tasks such as bomb detection, checkpoint inspections, and identifying chemical, biological, or radioactive threats. One standout feature is its ability to carry additional equipment and sensors weighing up to 150 pounds. Its manipulator arm can lift objects weighing as much as 330 pounds, enabling it to safely handle hazardous materials and perform bomb disposal without risking human lives. The FLIR Cobra is equipped with high-resolution cameras, including infrared and thermal sensors, allowing it to detect threats invisible to the human eye. These advanced visual tools provide a detailed and accurate understanding of the surrounding environment, enabling remote operation and enhanced situational awareness. Furthermore, its remote control system incorporates advanced security features and anti-jamming technology, ensuring safe and effective performance in combat scenarios while protecting operators from potential dangers. What sets the FLIR Cobra apart is its ability to navigate complex terrains, including stairs and rugged obstacles, making it indispensable in hazardous or hard-to-reach locations. Its advanced sensors can accurately detect chemical, biological, radiological, and nuclear substances, helping to address threats from weapons of mass destruction. This capability underscores its vital role in enhancing security and military effectiveness. Similarly, the T360 M2 MUT, or Multi-Utility Tactical Transport, co-developed by Precision Remotes and General Dynamics Land Systems, is another groundbreaking addition to military robotics. This autonomous combat vehicle combines versatility with unmatched performance. Equipped with a hybrid engine, it can seamlessly switch between wheels and tracks, enabling it to tackle a wide range of terrains, from smooth roads to rugged landscapes, deserts, and swamps. The T360 M2 MUT has a payload capacity of 433 kilograms, allowing it to transport military equipment, assist in rescuing wounded soldiers, and provide logistical support. Its drivetrain options, including 4x4 or 8x8 configurations, enhance its adaptability in combat environments. Additionally, this robot can operate continuously for 72 hours without refueling or travel up to 97 kilometers on a full tank with a maximum speed of 11 kilometers per hour. These features make it a reliable and efficient asset in military campaigns, reducing the reliance on human personnel while increasing operational effectiveness. Both the FLIR Cobra and T360 M2 MUT highlight the potential of robotic systems to revolutionize military operations. By taking on dangerous and demanding tasks, these machines not only enhance efficiency, but also protect human lives. Could these advanced systems one day replace humans entirely in tasks like bomb detection and disposal? The future of military robotics seems promising. In long-term operations or situations where soldiers cannot access certain areas, the T360 M2 MUT offers both automation and remote operation, providing flexibility in deployment and mission execution. This advanced robot is designed to operate in hazardous environments, such as contaminated zones, areas with landmine threats, or harsh conditions inaccessible to humans. By doing so, it reduces risk to soldiers and ensures missions can be carried out more safely. The T360 M2 MUT is also equipped with a staple gun mount carrying an M2 Browning machine gun, enhanced with an automatic target search and detection system. This makes it an effective combat support tool, capable of defending critical areas or assisting in offensive and defensive operations. As robotics and artificial intelligence continue to advance rapidly, the T360 M2 MUT is poised to become a vital asset in military missions, boosting combat efficiency while minimizing risks to personnel. Will robots like the T360 M2 MUT ultimately replace or complement soldiers in completing missions more safely and effectively? With the pace of technological evolution, answers may arrive sooner than expected. Military robotics are steadily progressing from simple transport devices to powerful combat tools. The future of warfare may not rely solely on heavy weaponry or fighter jets, but increasingly on intelligent robots. Are we witnessing the dawn of a new military era where robots play an essential role? As advancements continue, one can only imagine the capabilities of the next generation of these weapons. Something extraordinary is about to take flight in the world of aviation. Breaking free from traditional designs and their limitations, the groundbreaking X-65 aircraft is equipped with advanced technology and a bold vision, introducing an entirely new set of capabilities to the skies. What sets this marvel apart from its predecessors? How is it set to defy the previously laid-down rules of aviation? Join us as Aviation, a new aircraft with features and capabilities that brutally break the rules of aviation. An exceptionally mind-blowing advancement in aviation is just around the corner with the introduction of something entirely different from the regular. The X-65 equipped with something interestingly transformative. This experimental unmanned aerial vehicle will challenge everything about flight. For decades, traditional aircraft have relied on moving parts like rudders, flaps, and elevators to navigate the skies, limiting their aerodynamic efficiency and stealth potential. The X-65, however, aims to break free from these constraints with a game-changing technology known as Active Flow Control, or AFC. The X-65 is an exciting, uncrewed aircraft that will push the limits of aviation technology. With a wingspan of 30 feet and a gross weight of 7,000 pounds, this aircraft is designed to fly at speeds of up to Mach 0.7, making it capable of impressive performance. Its size and speed will closely resemble that of a military trainer aircraft, which ensures that the data gathered from its flight tests will be directly relevant to the development of real-world aircraft. This alignment with existing military aircraft design allows engineers to draw meaningful conclusions that can accelerate the evolution of future technologies. One of the X-65's most striking features is its diamond-shaped wings. This unique design is not just for show. It is engineered to optimize learning and testing for AFC, or Active Flow Control technology. By testing this innovative wing shape in actual flight conditions, The X-65 will provide valuable insights that could change the approach to future aircraft design. Beyond its immediate purpose, the X-65's modular platform design adds an extra layer of versatility. It is a crucial test asset for the Crane program and can support future experimental projects with DARPA and other agencies. This adaptability means that the X-65 could play a significant role in shaping the future of aviation technology, far beyond its initial mission, contributing to a wide range of groundbreaking projects. So what is active flow control, and how does it help change military aviation? Active flow control is a sophisticated technique that allows aircraft to manipulate airflow precisely. Traditional methods like vortex generators are passive and static, altering how air moves around the aircraft. Active flow control, however, takes a more innovative, more dynamic approach. By releasing controlled bursts of air through specialized nozzles, it actively adjusts the pressure of the boundary air surrounding the plane. This real-time control creates a more efficient and adaptable performance profile, paving the way for dramatic improvements in flight capabilities. The concept of active flow control has its roots in early 20th century research. In 1904, the German scientist Ludwig Prandtl made a key discovery about the boundary layer, a thin layer of air next to a surface, and showed how suction could help control airflow and prevent separation. This was a significant step in understanding how to manage airflow over aircraft wings and other surfaces. However, it wasn't until 1947 that a breakthrough occurred, thanks to the work of Schubauer and Skramstad. They introduced unsteady flow control beyond Prandtl's steady suction approach. Their method used periodic excitation or controlled bursts of energy to actively manage the flow of air. This innovation allowed researchers to overcome efficiency barriers that had previously limited the performance of aircraft and other vehicles. Today, active flow control continues to evolve, offering exciting potential for improving the efficiency and performance of modern aviation systems. Military aircraft, drones, and missiles are on the brink of a revolutionary transformation, thanks to active flow control technology advancements. This advanced innovation could enable them to travel much farther using the same amount of fuel, making them more efficient and versatile than ever before. Active flow control nozzles are being developed to be lighter, simpler, and more fuel efficient than traditional control systems that rely on moving surfaces. These advancements promise to extend aircraft range, boost agility, and cut maintenance demands and manufacturing costs. A glimpse of active flow control's potential came during NATO's 2018 tests, when drones with the technology displayed remarkable agility, responding even more dynamically than expected. These tests showed how AFC could dramatically enhance the maneuverability and efficiency of future aerial systems. If active flow control components remain lightweight, streamlined, and stealthy, they could be a game changer for modern jet fighters and other aircraft. Reducing radar visibility while improving performance makes AFC particularly attractive for military aviation, where stealth and efficiency are critical. Projects like Crane and control of revolutionary aircraft with novel effectors are at the forefront of this development. Spearheaded by experts in the field, Crane aims to make AFC technology affordable and practical for widespread use. The program's manager, Richard Lezian, emphasized how the X-65 platform could be a testing ground for various airflow control experiments. This includes potentially integrating active flow control innovations into next-generation designs like BAE Systems' Magma drone, which is already exploring futuristic flight concepts. In late 2020, Aurora Flight Sciences undertook an ambitious challenge. They partnered with another technological powerhouse, DARPA, to develop experimental aircraft under the Crane, or Control of Revolutionary Aircraft with Novel Effectors program. This wasn't just another aircraft program. It was explicitly aimed at changing how planes fly by pioneering active flow control. This technology uses air manipulation instead of traditional moving parts for control. The project began with Phase 0, where Aurora worked alongside Boeing and the University of Arizona to lay the groundwork. Phase 0 was not yet about building the aircraft. It focused on creating the tools and methods needed to integrate active flow control into the earliest stages of aircraft design. This step was essential to ensure that the bold idea of replacing mechanical control surfaces with active flow control was practical and effective. By August 2021, the project entered Phase 1, which brought the concept closer to reality. This phase involved a flurry of activity, defining system requirements, sketching preliminary designs, developing sophisticated software, and conducting initial airworthiness evaluations. The team took the project to a wind tunnel in San Diego, California, to validate their designs in May 2022. These tests provided critical data, helping engineers refine flight control laws centered on AFC. It was a significant moment, as the results confirmed that the technology had the potential to redefine aircraft control systems. The momentum didn't stop there. In December 2022, DARPA allocated funding for the detailed engineering of a full-scale X-plane. This marked the start of the second phase, where Aurora could dive deeper into the complex details of turning their vision into a real aircraft. The funding also opened the door to the possibility of building and testing the aircraft in future phases, making the dream of an active-flow, control-powered X-plane one step closer to reality. Then, in January 2022, Aurora Flight Sciences made a major leap and reached an exciting milestone. DARPA selected the company to construct a full-scale X-plane for Phase 3 of the Crane program. This wasn't just another aircraft. It was a marvel of innovation that no one would have envisioned in the past. The design ditched traditional moving control surfaces like flaps and ailerons and relied entirely on active flow control actuators to steer and stabilize the plane. This approach promised to make aircraft lighter, more efficient, and stealthier. The Crane program's X-plane would demonstrate the power of active flow control and pave the way for future aviation technologies that could reshape the industry. For aviation enthusiasts, this project symbolizes the spirit of innovation and the boundless possibilities of pushing the limits of what aircraft can do. DARPA plans to construct and fly a 7,000-pound X-plane with active flow control technology. This full-scale aircraft will address the most demanding challenges of using active flow control for controlled flight while integrating modular wing designs to allow for future testing of advanced systems. Although the initial demonstrator aircraft will be limited to a maximum speed of Mach 0.7, approximately 537 miles per hour, it holds tremendous innovation potential. The insights gained could make this technology a national asset for aerospace research, paving the way for more efficient, versatile, and innovative aircraft designs. However, what's catching the eye of aviation enthusiasts is DARPA's recent reveal of concept art for the X-65. The images have drawn comparisons to the legendary X-Wing starfighter from Star Wars, thanks to the aircraft's unique double-wing design when viewed head-on. While the resemblance fades from other angles, it's still enough to excite aviation and science fiction fans. What truly sets this drone apart is its departure from traditional flight controls. Aviation has relied on moving parts like rudders, flaps, and ailerons for over a century to guide aircraft through the skies. This drone eliminates all that. Instead, it uses precise bursts of compressed air to execute intricate maneuvers. These air jets act as invisible control surfaces, directing the aircraft without conventional systems' added weight or mechanical complexity. This breakthrough simplifies design and opens doors to lighter, more efficient, and stealthier aircraft. By eliminating moving surfaces, the X-65 would face less drag, which simply means the aircraft would have a smoother and more efficient flight. It's also better suited for high-angle maneuvers, pushing the boundaries of what aircraft can achieve. The system even allows for thicker wings, which add structural strength, provide more room for fuel, and simplify high-lift mechanisms, crucial for improved takeoff and landing performance. Testing for the demonstrator is scheduled to begin in 2025, and anticipation is building. With its potential to eliminate traditional control surfaces and create sleeker, more efficient planes, the active flow control technology being tested on the X-65 could represent the future of aviation. For now, enthusiasts and experts eagerly await the next phase of this thrilling journey into uncharted skies. From available images, the X-65 relies on a single jet engine with an air intake underneath its fuselage. Interestingly, an upper intake and exhaust are likely part of a system that provides compressed air for its 14 nozzle banks spread across the airframe. These nozzles are key to the AFC system, enabling precise airflow manipulation for advanced control without traditional flaps or ailerons. Another standout feature of the X-65 is its modular design, which offers unmatched flexibility for future testing and innovation. DARPA has emphasized that the aircraft can accommodate wings with different shapes and degrees of sweep. It can also integrate AFC systems developed by other companies, making it a collaborative platform for cutting-edge technologies. This modularity ensures that the X-65 isn't just a single experiment, but a dynamic testbed that will evolve as new ideas and technologies emerge. Researchers are pushing the boundaries further by exploring advanced methods like plasma effectors, which use ionized gases to control airflow. These futuristic technologies could refine active flow control and make it even more effective. The ultimate goal? Eliminating the drag-inducing surfaces that slow planes down and increasing their visibility to radar systems. For military aircraft, this is a game-changing development. Stealth is critical when operating in contested airspace, especially against modern radar-guided missile defenses. Reducing aircraft's radar cross-section, including non-combat planes like refueling tankers and cargo transports, can mean the difference between mission success and failure. Consider the iconic B-2 stealth bomber, which already tackles these challenges with an innovative design. By eliminating the tail fin and rudder, the B-2 relies on intricate flight control systems to manage stability and maneuverability. Yet even the small movements of its control surfaces, like flaps, can slightly increase its radar signature, making it more detectable. Active flow control holds the promise of eliminating these vulnerabilities. Future stealth aircraft could rely on active airflow management instead of physical control surfaces, creating a sleeker, more radar-resistant profile. The benefits of active flow control aren't limited to the military world. Commercial aviation stands to gain immensely from this technology. Reducing drag doesn't just make planes faster, it also makes them more efficient. Airlines are constantly seeking ways to improve fuel economy, and even a minor increase in efficiency can result in significant cost savings. For passengers, this could mean longer non-stop flights and lower ticket prices. For the environment, it means reduced carbon emissions and a greener future for air travel. One thing is certain, active flow control is rewriting flight rules, not just for traditional plane, but for revolutionary vertical lift vehicles. As airlines embrace efficiency and eco-friendly travel, these advanced machines are breaking boundaries, redefining what's possible in air mobility. From futuristic air taxis to massive cargo drones, the future of flight is poised to take off in ways we never imagined. With their incredible ability to take off and land anywhere and hover in place, vertical lift vehicles are transforming how we think about air travel. These advanced machines are being considered for exciting new roles far beyond the traditional uses of helicopters. NASA's Revolutionary Vertical Lift Technology, or RVLT project, is collaborating with government agencies, industry leaders, and universities to develop cutting-edge technologies that could revolutionize air travel. This includes futuristic concepts like air taxis for passengers and ample cargo drones. As these markets are projected to grow rapidly over the next decade, the success of vertical lift vehicles will depend on creating designs that are safe, reliable, cost-effective, and quiet enough to gain community acceptance. The Revolutionary Vertical Lift Technology project is dedicated to making this vision a reality by ensuring these vehicles can operate safely, reducing their environmental impact, especially noise, and expanding access to sustainable transportation options that can boost the economy. Although the Revolutionary Vertical Lift Technology project has traditionally focused on advancing helicopter technology, it is now focusing on innovative vertical lift designs of various sizes and missions. These efforts are aimed at supporting advanced air mobility and unlocking the next generation of air travel. The sky is no longer the limit, it's just the beginning. The Revolutionary Vertical Lift Technology project is diving into exciting research areas to shape the future of advanced vertical lift vehicles. For cleaner and more efficient propulsion, RVLT is working on next-generation electric systems to make future aircraft faster, more reliable, and operationally efficient. This includes exploring how to manage heat and power in electric setups, designing longer motors, and studying how different electric propulsion systems work for various aircraft sizes. The project also focuses on improving powertrain technology for electric and hybrid electric vehicles. To make vehicles quieter and more efficient, Revolutionary Vertical Lift Technology is tackling the issue of noise, which has been a growing concern with helicopters. They're combining better flight practices with advanced rotor designs and human factors research to cut noise levels in half for standard VTOL vehicles. New tools are being developed to predict noise for electric VTOL concepts, letting designers balance performance and noise reduction. RVLT is also looking at how fleets of these vehicles might affect communities in creating ways to assess and minimize their collective noise impact. Safety, comfort, and accessibility are other significant priorities. Revolutionary vertical lift technology is working to make AAM vehicles safer in crashes by studying occupant protection and improving the strength of composite materials. They're also collaborating with experts to use innovative materials and methods to address icing problems unique to vertical lift vehicles, like ice shedding from blades. On the comfort side, revolutionary vertical lift technology explores how these vehicles handle the air, how passengers react to motion, and what makes cabins more pleasant. Research into better control systems, pilot workload, and passenger comfort is paving the way for a smoother and safer flying experience. The RVLT project is also working on creating advanced tools to predict how VTOL, or vertical takeoff and landing aircraft, will perform and how much noise they will make, especially for designs with multiple rotors or propellers. This capability is crucial for designing innovative aircraft that can be balanced and controlled in new ways. To achieve this, NASA's revolutionary vertical lift technology is developing detailed models that focus on different aspects of aircraft design, such as the sources of noise, the structure of rotor blades, and the way these vehicles behave in flight. Real-world data from tests on components like rotors and propellers will back these models. These tests will examine how multiple rotors interact with each other and the aircraft's body, providing valuable insights into noise and performance. The results will help refine designs, balancing quiet operation with high efficiency. The project also includes conceptual design studies, exploring various aircraft configurations to find the best trade-offs between noise levels and performance. These designs will be improved using data from tests and advanced analyses, ensuring they are as accurate and practical as possible. RVLT's efforts go beyond just developing tools and models. They are deeply invested in fundamental research for vertical lift technology. This work is carried out with key partners, including the U.S. Army Combat Capabilities Development Command, Aviation and Missile Center, and the U.S. Navy Office of Naval Research. These organizations support the Vertical Lift Research Centers of Excellence. From 2016 to 2021, these research centers were led by prestigious institutions like Georgia Institute of Technology, Pennsylvania State University, and the University of Maryland, along with their partners. These teams bring together top researchers to study cutting-edge technologies that will shape the future of vertical lift aircraft, ensuring continued innovation and progress in this exciting field. By combining advanced modeling, rigorous testing, and collaborative research, RVLT is paving the way for quieter, more efficient, and more innovative VTOL aircraft designs that could transform human perceptions of air travel. Throughout history, nations have used their navies to demonstrate strength on the water. Whether in warm seas or up in the Arctic, controlling ocean routes is essential for any major power. These days, though, raw strength isn't enough. Military forces need to adapt quickly. This means the U.S. military must prepare for many different scenarios, from combat in freezing waters to operations near coastlines and through busy sea routes. How can the U.S. military make sure its troops are prepared to handle anything? Join us as we explore advanced technologies, amphibious strategies, and Arctic training that drive U.S. military mobility. Near Somalia's coast, pirates are clashing with U.S. Navy ships. Despite facing America's advanced military vessels, these armed pirates keep launching attacks. They've gotten comfortable operating in these uncontrolled waters. Even though they are outmatched by the Navy's superior equipment and training, the pirates continue their bold attempts anyway. No matter how advanced the Navy's ships are, they still have to deal with tiny, fast-moving skiffs full of armed raiders getting way too close for comfort. And the pirates, with nothing to lose, are counting on that moment of shock to give them an edge, even against a military Goliath. So, what's the answer? Beating erratic pirates takes more than raw strength. The Navy also has to be quick and smart to take control of a crazy situation. Somalia's problems started in the 1990s when its government fell apart. With no one in charge, the country became unstable. Foreign ships took advantage by fishing illegally in Somali waters and dumping waste there. This left many local fishermen without a way to earn money. Some of these fishermen then turned to piracy to survive. At first, they went after small ships passing by to make quick money. As they got bolder, they started targeting bigger ships, even ones with security. These weren't your storybook pirates with parrots and eye patches. They were organized and smart. They had lookouts watching for ships and planned their attacks carefully. Before long, ship captains everywhere were taking the long way around just to avoid them. The pirates had it down to a science. They would use small, fast boats to sneak up on huge ships. Their spies would tell them just where to hit and when. Once on board, the pirates would take the crew hostage and demand massive ransoms. The pirates were driven by a desperate need for money, but they were also master planners. They knew how to pick their targets and play the odds. Even against ships with armed guards, they would find ways to get the upper hand. So it was not just reckless attacks. There was a method to the madness. The pirates made ships start traveling in convoys and hiring more security. But there was only so much the ships could do. In the end, they were still vulnerable to pirates who were willing to do anything for a score. In 2009, Somali pirates attacked a United States cargo ship called the Maersk Alabama. It was the first time in 200 years that pirates had gone after an American ship. The crew fought back hard. The captain, Richard Phillips, gave himself up as a hostage to protect his crew. The hijacking made headlines around the world. The United States Navy sent in a warship called the USS Bainbridge. They also sent in their top gun, Navy SEAL snipers. The mission was to rescue Captain Phillips, no matter what. The Navy found the pirates holding Phillips in a lifeboat. The pirates were armed, desperate, and refusing to back down. But the SEALs were ready. When they saw their chance, the snipers took their shots. In seconds, it was over. 3 pirates were dead. Captain Phillips was safe. Against a small army of elite American fighters, the pirate gang never really had a chance. The rescue sent a clear message. The United States would go all out to protect its ships and crews. No matter how daring the pirates were, they could not beat the most powerful navy on Earth. From that point on, pirates knew they were picking a fight with a superpower if they messed with American ships. A Navy officer who fought pirates once said something interesting. He noted that the Navy doesn't just start shooting right away. And that actually made the pirates bolder. They figured they could usually get a ransom or a deal before the Navy got tough. Basically, the pirates were betting on the Navy holding back. They knew the Navy had the power to blow them out of the water. But they gambled that the Navy would negotiate first and shoot later, if at all. Somali pirates are bold, but they are totally outmatched against United States warships. Ships like the USS Howard and USS Bainbridge are tricked out with high-tech gear. They have radar and sonar to spot pirates from miles away. Their weapons are super accurate, and their crews train non-stop to handle worst-case situations. For the pirates, every attack is a huge gamble. If they are lucky, they could score a big payday. But if they mess with the wrong ship, it could be game over. Picture a tiny speedboat full of guys with AK-47s. Now imagine them trying to take on a billion-dollar destroyer armed to the teeth. The pirates have guts, no doubt, but guts only take you so far against guided missiles and elite sailors. As Somali piracy got worse, the United States Navy took the lead in fighting back. But they did not just start blasting away at the pirates. Instead, the Navy focused on ways to stop attacks without anyone getting hurt. The Navy knows it could easily sink the pirates' boats, but that would put hostages and even the pirates themselves at risk. So the goal is to shut down attacks while keeping everyone safe. The Navy uses things like sound cannons that blast the pirates with noise. They shoot special nets to tangle up the pirates' boats so they can't move. When they have to, the Navy sends special forces teams to board the hijacked ships and take control. Here are some of the Navy's favorite pirate-stopping gadgets. The first is the LRAD. This beautiful technology blasts loud sound waves at the pirates. The noise is so intense, it drives them away without actually hurting them. The second one is the water cannon, which is a superb water gun that they use to create a wall of water between their ship and the pirates. The blast usually floods the pirates' boats and makes them sink. Another interesting weaponry is the stun grenades. These are special grenades that don't cause real damage. When they go off, they make a bright flash and a loud bang. It stuns and destabilizes the pirates for a minute so the Navy can move in. Other weaponry on this list is the electric barriers and stun guns. With this technology, the Navy can set up electric fences on the sides of their ships. If the pirates try to climb on board, they will be electrocuted. The stun gun shoots electricity to zap pirates from far away. The last on the list is the laser and light weapons. These sci-fi style weapons shoot intense beams of light. They can temporarily blind the pirates or make them feel like their skin is on fire. So yeah, the Navy has some wild ways to stop pirates without killing them. They're all about using high-tech gadgets to shut down attacks while keeping things as safe as possible. It's pretty crazy what they've come up with. Back in April 2010, the USS Nicholas was out on patrol in the Indian Ocean. The crew spotted a suspicious little boat nearby. Turns out it was full of pirates. These pirates had gotten audacious after pulling off some other hijackings. They figured that they could take on anyone. Big mistake. In a move that would come back to haunt them, the pirates took a shot at the Navy ship. The USS Nicholas wasn't messing around. They fired back and went after the pirate boat. The Navy used its special tools and tactics to stop the armed pirates and capture them. On the boat, they found bullets and extra fuel. This showed the pirates were ready for a long fight, so the Navy sank their boat. They kept investigating and found 2 more pirates on a bigger ship. They got them too. The actions of the pirates have captured attention and have sparked intense debates. Some people think the Navy needs to get tougher on pirates. They say that if pirates attack in international waters, the Navy should just start shooting to send a stronger message. The idea is that pirates would think twice if they knew they would get blown away immediately. If the Navy made some extreme examples out of a few pirate crews, the rest might decide it's not worth the risk anymore. The debate really comes down to deterrence. What would make the pirates back off for good? Is it measured with restraint and precision? Or is it the fear that if they mess with the wrong ship, they are guaranteed to end up dead? It is a complex issue with a lot of moving parts. But some folks think that if we ever want to see the end of Somali piracy, the Navy might need to put the kid gloves away and start delivering some harsher consequences, even if it means more sunken skiffs and pirate casualties in the short term. The Navy has a different take, though. They want to be tough on pirates, but they also want to be humane. The goal is to stop piracy without innocent people getting hurt by mistake. So far, the Navy's tactics seem to be working. There's a lot less piracy than there used to be, and the Navy has kept the oceans mostly safe, all without causing a bloodbath. At the end of the day, the Navy is trying to thread a needle. They need to be strong enough to beat the pirates, but they also want to solve the problem without going overboard and causing unnecessary tragedy. The pirates off Somalia's coast aren't just criminals. They are people pushed to extremes by a broken system. Their country has no real government, most people live in poverty, and foreign ships have been overfishing their waters for years. Sure, more military patrols have made pirate attacks less common these days, but that's just putting a band-aid on the real problem. The hard truth is that until Somalia gets back on its feet with a working government and ways for people to make an honest living, some will keep turning to piracy because they see no other choice. The United States Navy stays ahead by using top-notch tech. Take their newest ships, the Zumwalts. These destroyers pack some serious punch. They can launch missiles that fly over 5 times faster than sound. Back in 1991, they started using Arleigh Burke destroyers, and these ships are still going strong today. They are like Swiss Army knives on the water. They can handle threats from above, on the surface, or underwater. A big reason they work so well is their Aegis system. It spots and tracks threats super fast, then takes them out in seconds. Fighting pirates takes teamwork between different countries. The International Maritime Bureau keeps track of attacks and shares info with governments. There's also the United Nations Agreement that spells out how countries can work together to catch and prosecute pirates. This helps everyone coordinate instead of trying to handle it alone. Teams of ships from different countries work together to keep key shipping lanes safe, including the Gulf of Aden, Arabian Sea, and Indian Ocean. This group, called Combined Task Force 150, doesn't just fight pirates, they also stop smugglers and terrorists. The United States Navy plays a big part in this team effort. One example is the USS Howard, which has helped protect ships that pirates tried to take over. Not every country has the tech and money the United States Navy has to fight pirates. Some struggle because they do not have enough funds, their coastlines are hard to patrol, or they don't get much help from other nations. That is where the U.S. Navy steps in. They don't just protect American ships. They help keep all trade routes safe for everyone. Despite having impressive technology, the United States technology has a long way to go. This is because modern weapons are way scarier than pirates when it comes to global threats. Take, for instance, the ICBMs. The ICBMs are serious business. They are missiles that can carry nukes across the world with scary accuracy. Russia's newest one, the Satan II, is especially concerning. It is not just super powerful, it can also carry special vehicles that fly so fast and low that the United States defense systems have trouble spotting them. That has got a lot of people worried, even countries with top-notch military tech. The RS-28, also known as the Satan II, packs an unreal amount of firepower. It can carry up to 10 big warheads, 16 smaller ones, or 24 super-fast glide vehicles. To give you an idea of how powerful it is, one Satan II has about 400 times the destructive force of the bomb dropped on Hiroshima. The Satan II can hit anywhere in the United States. It can fly over 11,000 miles. What makes it so tough to stop is all its tricks. It uses fake targets to confuse defense systems, so the usual ways of shooting down missiles don't work well. This thing is crazy fast too. It can go about 16,000 miles per hour. And here's the really scary part. It can split up in the air, sending warheads to hit different targets hundreds of miles apart. They built this missile to be light but tough, using special metal mixes like aluminum and magnesium. This makes it harder for radar to spot. Plus, it can launch these super-fast gliding weapons that can switch direction in midair. These hypersonic glide vehicles are changing how modern weapons work. They fly more than 5 times faster than sound, which is unbelievable. But it is not just their speed that makes them dangerous. Regular missile defenses can't handle them because they can change direction mid-flight. Think about trying to catch something that's not only super fast, but can zigzag wherever it wants. It's like trying to swat a bee that can teleport. Most missiles follow a simple up and down path, like throwing a ball. But these HGVs, they can fly low and switch direction whenever they want. That's why they're so hard to stop. When you put these glide vehicles on the Satan II, you get a weapon that can slip past just about any defense system out there. North Korea's got their own scary missile, the Hwasong-17. While it's not as big as the Satan II, it's still powerful enough to hit anywhere in the United States. It can fly about 9,300 miles and carry nuclear weapons. This missile has some tricky features. It can also change its path while it's flying, and it has enough range to hit major cities like New York, Washington, D.C., or Los Angeles. That is a big deal because it shows North Korea is getting better at making dangerous weapons. These new missiles are exposing some big problems with our defense systems. The old systems were built to stop missiles that flew in a simple arc, but these new ones are different. They're faster, can change direction, and use tricks to confuse our defenses. Right now, we've got ground-based interceptors in Alaska and California to shoot down long-range missiles. We've also got Navy ships with Aegis systems that can move around to where they're needed, but neither of these is great at stopping the new hypersonic weapons. We're working on better interceptors, but they won't be ready for years. So what does the United States need to do? First, they need to build better tech to stop these missiles. Second, they need to figure out how to track and hit those super-fast glide vehicles. Third, they need to get countries to work together on defense and arms control. Speaking of North Korea, their Hwasong-17 missile is a big deal that has everyone worried, especially since the United States' current defense systems might not be able to stop it. The bottom line is, the game is changing. The United States' old ways of stopping missiles might not cut it anymore. They need new solutions. The Hwasong-17 is giving U.S. missile defense teams a real headache. The United States main defense system, called GMD, has 44 interceptor missiles split between Alaska and California. But there's a catch. It's not as strong as it sounds. Here's why. The United States needs to shoot 4 interceptors at each incoming missile to have a good chance of stopping it. Do the math, and that means we can only handle 11 attacks at once. That's where things get scary. The Hwasong-17 can carry up to 4 warheads, plus it throws in fake ones to trick defenses. If North Korea fired several of these missiles at once, the United States system could get swamped. To tackle these problems, the United States is working on several new ways to stop missile attacks. They are building better radar systems that can tell real missiles apart from fake ones. They are also planning to put interceptors on satellites to shoot down threats from space, giving them more coverage to protect against attacks. New technology includes laser weapons that could stop fast-moving missiles. Meanwhile, their research teams are developing faster, more agile interceptors to improve their chances of hitting incoming threats. The F-35A is more than just a fighter jet. It's the perfect symbol of the United States' air dominance. Designed during a time when the United States demanded the highest level of air security, this aircraft redefined aerial combat with its unmatched capabilities. But does it live up to the hype? What sets the F-35A apart from every other jet in the sky? Join us as we reveal the capabilities of the most advanced hypersonic jet in the world. The F-35 emerged as a result of the Joint Strike Fighter program, which was born from the consolidation of various military aircraft development projects in the 1980s and 1990s. One of these programs, the Advanced Short Takeoff/Vertical Landing, ran from 1983 to 1994. Its goal was to create a replacement for the U.S. Marine Corps and the United Kingdom's Royal Navy's Harrier jump jet. As part of Advanced Short Takeoff/Vertical Landing, Lockheed Skunk Works developed a stealthy supersonic fighter, which incorporated the shaft-driven lift fan system for vertical lift. The concept involved a single-engine aircraft with a canard delta wing, weighing around 24,000 pounds. In 1993, Advanced Short Takeoff/Vertical Landing was renamed the Common Affordable Lightweight Fighter, and collaboration expanded to include Lockheed, McDonnell Douglas, and Boeing. The end of the Cold War in 1991 and the collapse of the Soviet Union led to significant cuts in defense spending, which impacted military programs. The U.S. Department of Defense restructuring led to the cancellation of several aircraft programs, including the U.S. Air Force's multi-role fighter and the U.S. Navy's Advanced Attack/Fighter projects. The MRF, designed to replace the F-16, was postponed due to the changing defense needs and a reduced role for the F-16. Meanwhile, the A/FX program, originally intended to replace the A-6, was modified after the cancellation of its predecessor, the A-12 Avenger II, in 1991. Following the review of defense priorities, both MRF and A/FX were canceled in 1993. However, insights from these programs contributed to the formation of the Joint Advanced Strike Technology Program, aimed at developing advanced warfare technologies rather than a new aircraft. In 1994, the Astoval-CAF and JAS programs merged, as the requirements for a concept demonstrator aircraft became evident. This led to the creation of the Joint Strike Fighter program in 1995, which sought to replace a variety of multi-role and strike fighters. International collaboration was a key element from the outset, with the United Kingdom becoming a founding member and contributing to the program. Other nations, including Italy, the Netherlands, and Canada, joined during the concept demonstration phase, with varying levels of involvement. By 1997, Boeing and Lockheed Martin were selected to develop concept demonstrators for the JSF, with their respective aircraft designated X-32 and X-35. Lockheed Martin's design built upon the technologies developed under the ASTOL program, including the innovative SDLF system, which allowed for short takeoffs and vertical landings. Unlike Boeing's X-32, which used a direct lift system, Lockheed's X-35 utilized a lift fan in the forward fuselage that could augment engine thrust for vertical flight. The X-35 was designed to accommodate 3 versions: a conventional takeoff and landing variant, a carrier-based version, and a short takeoff and vertical landing version. This commonality between the variants was a key feature of the design, with modifications made to suit each specific role, such as a larger wing for the carrier variant. The first flight of the X-35A took place on October 24, 2000, and was followed by a series of tests to assess its flight characteristics. After 28 flights, the aircraft was modified into the X-35B to demonstrate its STOVL capabilities, including hover and short takeoff and landing. The X-35C, which featured a larger wing for carrier landings, conducted its first flight on December 16, 2000. These successful tests demonstrated the capabilities of the JSF and set the stage for the next phase. In 2001, after extensive testing and evaluation, Lockheed Martin was chosen as the winner of the contract for the system development and demonstration phase of the JSF program. Additionally, Pratt & Whitney was awarded a contract to develop the F-135 engine for the F-35. The aircraft was given the F-35 designation, a surprise to many, including Lockheed Martin, which had expected the F-24 label. This marked the beginning of the F-35's development as a versatile, multi-role aircraft capable of meeting the needs of various military forces worldwide. The F-35 is a single-seat aircraft equipped with a powerful AESA radar positioned at the front. This radar can track and engage multiple targets simultaneously, both in the air and on the ground. A key feature of the aircraft is its distributed aperture system, which uses 6 infrared cameras mounted around the jet. These cameras create a 360-degree video feed that pilots can view on their visors, effectively giving them the ability to see through the aircraft and themselves during flight. Although primarily a missile warning system, it also serves as a backup for night vision, allowing pilots to see in complete darkness, including clouds, mountains, and other aircraft. Beneath the nose of the aircraft lies the electro-optical targeting system. This system uses infrared technology, similar to sniper or lightning pods, to identify and track ground and aerial targets. It provides precise coordinates to guide laser-guided bombs, enabling both planned and dynamic targeting of moving objects. The F-35 is often referred to as a supercomputer with wings because of its ability to dominate the battlefield. Designed to serve as a versatile platform, it can manage and share situational awareness across a 60-mile radius, coordinating with other aircraft and decision-makers to maintain battlefield control and enhance operational effectiveness. Stealth is a fundamental feature of the F-35, achieved through advanced design techniques and materials. The aircraft's radar cross-section is significantly reduced by the careful shaping of its airframe and the incorporation of radar-absorbent materials. Specific design choices, such as aligning edges, using continuous curves on surfaces, serrating skin panels, and concealing the engine face, contribute to reducing RCS. The F-35 also employs a diverter supersonic inlet that utilizes a compression bump and forward-swept cowl, removing the need for a traditional splitter gap or bleed system. This innovation further decreases the radar signature by redirecting the boundary layer away from the inlet duct. The F-35's RCS is described as smaller than that of a metal golf ball at specific frequencies and angles, making it competitive with the F-22 in terms of stealth. The aircraft's design, which draws on lessons from earlier stealth models such as the F-22, features a durable radar-absorbent fiber mat skin that requires less maintenance than previous coatings. Furthermore, the F-35 has reduced infrared and visual signatures, along with stringent controls over radio frequency emissions to avoid detection. Much of the work involves the radar system, which identifies targets and shares that information with others. A significant part of the aircraft's capabilities is found in its outer panels. Beneath these panels are advanced supercomputers and large sensors integrated into nearly every section of the plane's exterior. These technologies are complex, and even experienced operators may not fully understand all the systems. The aircraft's stealth is especially effective against high-frequency X-band radar, though it is vulnerable to low-frequency radars, which can detect stealth aircraft through Rayleigh scattering. However, low-frequency radars are less precise, more prone to interference, and generally more conspicuous. To further conceal its radar cross-section, the F-35 can also use Lundberg lens reflectors to obscure its signature. Moving on to the inside of the aircraft, the cockpit of the F-35 is designed to enhance situational awareness with a 20 by 8-inch panoramic touchscreen that displays vital flight and combat information, including flight instruments, store management, and caution warnings. This screen can be customized to the pilot's preference, with a smaller standby display positioned below it. A speech recognition system aids communication, and the aircraft does not use a traditional head-up display. Instead, all relevant data is shown directly on the pilot's helmet visor via a helmet-mounted display system, allowing the pilot to access information regardless of head position. The canopy is a single tinted piece hinged at the front for structural integrity, while the Martin Baker US-16E ejection seat is equipped with a twin catapult system. The aircraft uses a hands-on throttle and stick system and an onboard oxygen generation system powered by the integrated power package ensures life support with emergency backup systems in place. One feature people often find fascinating in fighter jets is their weaponry. The F-35A variant is unique as it includes an internal cannon located near the left air intake of the jet. This cannon can hold 181 rounds of 25mm ammunition. Although this is larger than the ammunition carried by most fourth-generation fighter jets, it is still smaller compared to what an A-10 uses. A valuable feature of this cannon is its burst-around limiter, allowing the pilot to control how many rounds are fired with each trigger pull. For instance, a pilot can choose to fire only 20 rounds at a time, ensuring better ammunition management. This setup allows for multiple precise shots during a mission. Beneath the jet, the bomb bay doors open to reveal its primary weapons storage area. Inside the bomb bay, the F-35 can carry bombs of varying sizes, ranging from 250 pounds to 2,000 pounds, depending on the mission's needs. For example, when targeting heavily fortified structures like bunkers or tanks, the 2,000-pound bomb might be used. Alternatively, for missions requiring precision against multiple targets, smaller bombs can be deployed to hit up to 8 separate locations within a 70-mile range. This flexibility makes the jet highly versatile and practical in diverse scenarios. The aircraft also features one of the most advanced flight control systems globally, comparable to that of the F-22 Raptor. Known as a fly-by-wire system, it is more sophisticated than the system used in the F-16 Viper. Essentially, this system interprets every movement of the pilot's controls, such as the stick and throttle, as a digital request, ensuring precise and efficient responses. When comparing the F-22 Raptor and the F-35, both being fifth-generation fighters, there are notable differences. The F-22 features twin engines, offering extraordinary maneuverability and superior thrust vectoring capabilities, making it ideal for air combat. Its larger airframe enhances its role as a dominant dogfighter. On the other hand, the F-35, a newer design by approximately a decade, is smaller and optimized for versatility. While it remains agile, it can carry larger payloads, including 2,000-pound bombs, compared to the F-22 1,000-pound capacity. Additionally, the F-35 is equipped to hold more air-to-air missiles internally, emphasizing its multifunctional air-to-ground and air-to-air capabilities. The F-35 Pratt & Whitney F-135 engine is among the most potent fighter jet engines ever created, producing an impressive 43,000 pounds of thrust in afterburner mode. This incredible power supports the entire demonstration, lasting about 13 minutes, and ensures reliable performance without concerns of engine failure during high-stress operations. Remarkably, the engine's thrust exceeds the aircraft's weight, enabling astonishing maneuvers, including spins and rapid direction changes. By about 2 minutes into a demonstration, the thrust-to-weight ratio allows for unparalleled agility, showcasing the F-35 engineering excellence. From that moment onward, the acceleration increases rapidly to the point where it becomes challenging to manage, especially at sea level or during a demonstration over a beach. For those unfamiliar, there are 3 distinct variants of the F-35, the A, B, and C models. The A model is the conventional version primarily used by the Air Force. It is designed for standard takeoff and landing, just like any typical airplane. The B model, used by the Marine Corps, is a short takeoff and vertical landing variant capable of hovering. Lastly, the C model is intended for carrier operations. It is launched via a catapult from aircraft carriers and lands using an arresting cable. It is fascinating to consider the experience of flying such an advanced machine. When piloting the F-35, and especially when another F-35 approaches alongside, one can't help but marvel at the aircraft's incredible design. One interesting fact is that at Hill Air Force Base, in the Aircrew Flight Equipment section of the 388th Operational Support Squadron, there is a special area dedicated to fighter pilot preparation, similar to a locker room for athletes. Just as sports teams gear up before an important game, F-35 pilots have a designated space to prepare themselves for flight. This area is where they store essential gear, such as G-suits, survival vests, and most notably their helmets. One of the key components of the F-35 cockpit system is the Vision System's International Helmet-Mounted Display. This system eliminates the need for a conventional head-up display by projecting all relevant data onto the pilot's helmet visor. Additionally, it provides night vision and infrared imagery through the distributed aperture system, enabling the pilot to effectively see through the aircraft. The system allows the pilot to target and fire missiles even when the aircraft is not directly aimed at the target, thanks to off-boresight missile seeker cues. Each helmet costs around $400,000, and while the system offers significant advantages, concerns have been raised about the potential risk to lightweight pilots during ejection due to the added weight of the helmet. Development of the HMDS encountered issues with vibration, sensor displays, and night vision during the testing phase, leading to the consideration of an alternative system based on the AN/ABS-9 night vision goggles. However, after further improvements to the baseline HMDS, the development of this backup system was halted by 2013. By 2016, a new Gen 3 helmet was introduced, offering enhancements like improved night vision, better display systems, and automated alignment, marking a significant milestone in the F-35 cockpit development. These helmets are remarkable, being the most advanced fighter pilot helmets ever created. They are integrated directly into the aircraft, replacing the traditional heads-up display found in older jets. Instead, all necessary flight data, including airspeed, altitude, heading, warning systems, and targeting information, is projected directly onto the helmet visor. In addition to the helmet, pilots also wear specialized gear to support them during flight. Below the neck, pilots are equipped with a G-suit designed to counteract the forces experienced during flight, ensuring blood circulation to vital areas to prevent loss of consciousness. Pilots also wear survival jackets, which contain essential equipment such as flares, flashlights, tourniquets, and GPS systems, all of which are vital if the pilot ever needs to eject from the aircraft. Finally, the oxygen mask connects directly to the aircraft to supply the necessary oxygen during flight, ensuring the pilot's safety and ability to function effectively. Comparing the F-35 with the Chinese J-20, these air fighters are two cutting-edge fighter jets, each boasting impressive strengths. The F-35 stands out for its superior stealth and widespread adoption among United States allies. At the same time, the J-20 is known for its speed and ability to target critical support aircraft, making it a serious contender. Despite the J-20's advantages, including supercruise capability and heavy investment in development, it lacks a cannon, and its pilots have limited combat experience. In a potential conflict over Taiwan, the F-35's stealth and the battle-tested expertise of U.S. pilots could give it an upper hand, though the J-20 remains a formidable opponent. The J-20, nicknamed the Mighty Dragon, officially joined China's Air Force in 2018, with around 150 currently in service. Its design closely resembles features of the F-35 and F-22, sparking speculation that China used cyber espionage to copy U.S. technology. Like the F-35 program, the J-20 has seen massive financial investment, costing an estimated $4.4 billion, with each jet priced at $120 million. With both nations mass-producing these fighters, a future clash over hotspots like Taiwan or the South China Sea seems possible. The question remains, which jet would reign supreme in this battle for air superiority? The J-20 is a powerful twin-engine fighter jet used by China. It currently flies with Russian-made AL-31 or Chinese WS-10C engines, but China is working to upgrade it with next-generation WS-15 engines for greater power and performance. However, progress on replacing the engines has been slower than expected. Despite this, the J-20 boasts impressive capabilities that make it a key player in modern air combat. With a top speed of Mach 2, a range of 1,100 nautical miles, and a ceiling of 66,000 feet, the J-20 is both fast and capable of covering long distances. It can carry a significant amount of fuel and is equipped to launch a variety of missiles, including air-to-surface and anti-ship types. This versatility allows the J-20 to excel in both ground attack missions and air superiority roles, enhanced by its thrust vectoring control and strong thrust-to-weight ratio. However, the J-20's stealth capabilities fall short when compared to the American F-35. The forward canards on the J-20 increase its radar visibility, giving the F-35 an advantage in spotting and engaging it first. Despite this, Chinese strategists believe the J-20 can still punch through contested airspace to target critical American support aircraft like tankers and reconnaissance planes. The newer J-20 models also include supercruise technology, allowing them to sustain high speeds without afterburners. This gives them an edge in speed over the F-35, which maxes out at Mach 1.6. The J-20's performance has drawn the attention of United States military leaders. Earlier this year, F-35s and J-20s came into proximity during an encounter over the East China Sea. General Kenneth Wilsbach, commander of the U.S. Pacific Air Forces, described the J-20's command and control systems as impressive, signaling that China's advanced fighter jet is not to be underestimated. As tensions rise over global skies, the world watches intently, and America's arsenal of defensive missiles stands ready to unleash unprecedented power. From the sky-splitting THAAD interceptors that leave no missile unscathed to the nearly mythical Patriot systems that can spot and strike from miles away, these weapons are designed to dominate. Can Russia's massive S-400 system withstand America's missile might? And when China's HQ-9s clash with missiles that can think, track, and strike on their own, will they stand a chance or crumble under pressure? Join us as we find out just how powerful the U.S. missiles are that can destroy Russia and China. Speaking of modern technology used in defense, a special category of weapons stands out: those that can find their target with great accuracy and speed. These weapons use advanced systems to guide and control their path, making them highly effective in defense and warfare. These weapons come in various forms, each built for specific tasks. Some are small and used in close-range battles, while others are much larger, designed to travel thousands of miles to reach distant targets. To make them work, engineers have created advanced systems that help guide these weapons to their destinations. For instance, some weapons called tactical types are built for short distances, like a battlefield. Others, called strategic types, are made to travel long distances and can even leave Earth's atmosphere before coming back down at incredible speeds. There are also different ways these weapons are launched. Some are sent from the ground, others from planes or ships, and some even from submarines hidden deep underwater. Each launch method has its unique design and purpose. A key feature of these weapons is how they move. Many use rocket engines that burn fuel to generate power. There are two main types of fuel: liquid and solid. Military designs often use solid fuel because it is safer to store and can be ready for use quickly. Once launched, the weapon needs to stay steady and accurate. To do this, engineers use fins and other parts to control its direction. Some designs use thrust vectoring, which means adjusting the rocket's exhaust to steer it. This is especially useful for those who travel into space. One of the most amazing parts of these weapons is their guidance system. This technology is like a brain that helps the gun find its target. Sensors on the weapon can detect heat, radar signals, or even images of the target. Based on what these sensors pick up, the guidance system adjusts the path to make sure the weapon hits accurately. For instance, some systems use infrared sensors to lock in the heat from a jet engine. Others can follow radar signals or even a visual image captured by a small camera. These systems make split-second decisions to correct the path, ensuring accuracy even at high speeds. For weapons that travel long distances, such as those used for strategic purposes, a different type of guidance system is used. Known as inertial guidance, this system measures the weapon's speed and position, constantly comparing it to where it needs to go. If it goes off course, the system makes adjustments to bring it back in line. Weapons are classified based on where they are launched from and the targets they aim to hit. Air-to-air weapons are fired from aircraft to engage other aircraft in flight, while air-to-surface weapons are designed to be launched from aircraft to strike targets on the ground or at sea. Surface-to-air weapons, on the other hand, are launched from the ground to intercept and destroy flying objects such as planes. Anti-ship weapons are specifically created to target and destroy enemy ships, while anti-tank weapons are built to penetrate and neutralize heavily armored vehicles. For long-range weapons, the classification shifts to their maximum travel distance. Short-range weapons can reach up to about 300 miles. Medium-range weapons extend their reach to distances between 300 and 600 miles. Intermediate-range weapons can travel up to 3,300 miles, covering significant distances to engage targets far away. Each category serves a distinct purpose and is designed with precision and efficiency in mind. The longest-range types are often launched from secure locations, like underground silos or mobile platforms. Some are even launched from submarines underwater, which makes them harder to detect. One example of advanced technology in this field is a system known for its reliability and flexibility. It includes a rocket with 2 stages for power and can fly at speeds of over 3 times the speed of sound, making it effective even against fast-moving targets. The system uses radio signals to guide the weapon and employs radars to track its target. Multiple radars, each with a specific job, support the guidance system. One radar detects targets from a long distance, while another helps track and guide the weapon during its flight. These radars work together to ensure accuracy, even against challenging targets. These technologies have changed the way defense systems work, making them faster, more innovative, and more accurate. By combining different types of propulsion, control, and guidance, engineers have created tools that can adapt to many challenges. Whether used to protect a country or support allies, these advancements are a vital part of modern defense strategies. With continuous improvements, including systems that can respond to hypersonic threats, this field remains an important area of innovation. Each new development helps make the world a safer place, showing how science and technology can be used to address complex problems. With missiles becoming faster, smarter, and deadlier than ever, a crucial question emerges. What defense system could stop a ballistic missile screaming down from space at over 15,000 miles per hour, nearly 20 times faster than a speeding bullet? The Terminal High Altitude Area Defense System, commonly known as THAAD, is one of the most advanced missile defense systems in the world. Designed by the United States, THAAD protects against short, medium, and intermediate-range ballistic missiles, especially in their final stages of flight when they are descending back toward the ground. Unlike traditional weapons, THAAD does not carry explosives. Instead, it uses its speed and force to collide with incoming missiles, destroying them on impact, a technology known as hit-to-kill. The idea for THAAD was born after the Gulf War in 1991, when Iraq used Scud missiles, exposing a need for better missile defense systems. Development officially started in 1991, and Lockheed Martin was chosen as the lead contractor. The system underwent years of testing, with early tests facing challenges. The first successful interception happened in 1999, showing the system's potential. THAAD operates using several key components. Each system includes a mobile launcher, advanced interceptors, a radar system, and a command center for control and communication. The radar, developed by Raytheon, plays a crucial role by detecting and tracking incoming missiles from far away. The entire system works together to identify threats, launch interceptors, and destroy missiles before they reach their target. The interceptors can reach altitudes of up to 93 miles and have a range of about 125 miles, giving THAAD the ability to protect large areas. Over the years, THAAD has been deployed in various regions, including South Korea, the United Arab Emirates, and Israel, as part of efforts to strengthen global missile defense. In January 2022, THAAD successfully intercepted a medium-range missile targeting the UAE, marking its first operational use in actual combat. The United States Army currently operates several THAAD batteries, each consisting of at least 6 launchers, 8 missiles per launcher, and support systems. Each battery costs around $800 million to produce. Lockheed Martin manufactures the interceptors in Alabama, while Raytheon builds the radar systems in Massachusetts. Efforts to improve THAAD are ongoing. For example, Lockheed Martin is exploring an extended-range version of the system to counter hypersonic threats, which are missiles that travel at incredibly high speeds and can maneuver unpredictably. This extended-range version would include a more prominent booster for greater reach. While still in the concept stage, the system shows promise for addressing future missile threats. THAAD is part of a layered missile defense strategy that includes other systems, such as the Navy's Aegis ballistic missile defense and the Army's Patriot system. Together, these technologies provide a multi-tiered defense, increasing the chances of intercepting threats at various stages of flight. Since its activation in 2008, THAAD has become a cornerstone of modern missile defense. Its ability to protect against evolving threats demonstrates how technology continues to evolve to meet global security challenges. With ongoing advancements, THAAD remains a vital tool in safeguarding nations from ballistic missile attacks. While THAAD excels at swatting down high-flying ballistic missiles, what happens when the threat comes from closer to home? From cruise missiles skimming the treetops, swarms of drones, or enemy aircraft trying to sneak through radar gaps? The Patriot Air Defense System, officially known as the MV-22 Patriot, stands as one of the most advanced missile defense systems in the world. Designed by the United States defense contractor Raytheon, it is built to safeguard large areas such as cities, military bases, and industrial zones from aerial attacks. The system has the remarkable ability to detect and track multiple targets at once, guiding its missiles to intercept potential threats with impressive accuracy. At the core of the Patriot system lies its radar, identified as the AN/MPQ-53 or AN/MPQ-65, which serves as the system's most crucial component. This radar is responsible for detecting enemy aircraft, missiles, or drones over long distances. Unlike earlier technologies that required several radars for different tasks, the Patriot system integrates all its functions into one. It scans the skies, identifies threats, and guides missiles to intercept them, all within a single platform. Another notable feature of the system is the missiles themselves. They are launched from mobile stations mounted on trucks or trailers, ensuring ease of transport and flexibility in deployment. These launchers carry various types of missiles, including the PAC-2 and PAC-3 models, which are engineered to intercept both high-speed aircraft and low-flying targets, such as drones or cruise missiles. The development of the Patriot system began in the 1960s, aiming to replace aging air defense systems of the time. By 1974, the system had achieved its first successful test of missile guidance, and by 1982, it was officially adopted by the United States Army. Over the years, it replaced older systems like the Nike Hercules and Hawk, establishing itself as the primary air defense technology. One of the system's standout qualities is its mobility. All its components, including the radar, command center, and missile launchers, can be dismantled and relocated in less than an hour. This flexibility allows it to respond quickly to changing battlefield conditions, making it a vital tool in modern military strategy. The Patriot system has been widely adopted beyond the United States, with countries such as Israel, Germany, and Japan incorporating it into their defense arsenals. Over time, the system has undergone significant upgrades. For example, in 2017, a new radar system called AN/MPQ-65A was introduced, offering 360-degree coverage and improved detection capabilities for more minor threats, such as drones. Technological advancements have also led to the use of materials like gallium nitride in the radar system. These materials enhance reliability and reduce the need for frequent maintenance, ensuring the system remains operational for extended periods. The Patriot Air Defense System plays a pivotal role in defending against aerial threats. Its advanced radar technology, precise missile guidance, and exceptional mobility make it a cornerstone of air defense for the United States military and its allies. With ongoing upgrades to meet modern challenges, it continues to demonstrate its importance in maintaining global security. From the cutting-edge advancements of the Patriot Air Defense System, we now shift our focus to a rival system with global significance: the Soviet and Russian air defense legacy. How does the formidable S-400 triumph compare to its Western counterparts? And why has it captured the attention of so many nations? The S-400 Triumph, often called the SA-21 Growler by NATO, is one of the most advanced air defense systems in the world. Developed in the 1990s by the Alma's Central Design Bureau, the S-400 was a significant upgrade to its predecessor, the S-300. It officially entered service in 2007, becoming the backbone of Russia's air defense network. What sets the S-400 apart is its versatility. This system is designed to intercept a wide variety of targets, including enemy aircraft, cruise missiles, and even ballistic missiles. It can also detect stealth aircraft, which are typically hard to track due to their radar-evading design. With its maximum range of 400 kilometers, about 250 miles, and the ability to hit targets at altitudes up to 30 kilometers, the S-400 can defend vast areas effectively. A single S-400 system can include up to 8 divisions, with each division controlling up to 72 launchers. This means one system can manage up to 384 missiles. These missiles come in 4 main types, each tailored for different ranges. The very long-range 40 and 6, which can reach 400 kilometers. The long-range 48 and 6, with a range of 250 kilometers. The medium-range 9M962 is capable of reaching 120 kilometers, and the short-range 9M96E has a range of 40 kilometers. This multi-layered capability allows the S-400 to counter threats at various distances and altitudes. One of the system's innovations is how it launches missiles. The S-400 uses a gas system to propel missiles up to 30 meters into the air before their rocket engines ignite. This design increases accuracy and extends the range, making it an efficient weapon against fast-moving targets. Russia has not only used the S-400 to enhance its military capabilities, but also as a strategic tool in international relations. The system has been sold to multiple countries, including China, Turkey, India, and Belarus. These deals often spark global debates, as the S-400's advanced technology can shift the balance of power in a region. For instance, Turkey's purchase of the S-400 created tensions with NATO allies, as they expressed concerns about compatibility with Western defense systems. Despite its impressive features, the S-400 is not without its challenges. For example, during the ongoing conflict in Ukraine, Ukrainian forces reportedly destroyed an S-400 launcher. This incident highlights that even advanced systems are vulnerable in modern warfare, where drones and electronic countermeasures play a significant role. The S-400's development also reflects the collaboration within Russia's defense industry. It involved contributions from key organizations like the Fakel Machine Building Design Bureau and the Novosibirsk Research Institute. This cooperation has resulted in a system that not only protects Russian airspace, but also serves as a symbol of its technological prowess. From the innovations of Soviet and Russian air defense systems, we turn our focus to China's HQ-9 system, a key player in modern air defense. How does this cutting-edge system compare to its global counterparts, and what makes it stand out? The Chinese HQ-9 is a cutting-edge air defense missile system designed to counter a wide range of aerial threats, including enemy aircraft, cruise missiles, helicopters, and tactical ballistic missiles. Built to perform under any weather conditions, day or night, the system is highly effective even in environments with intense electronic interference. This advanced capability makes it one of the most reliable components of China's third-generation air defense technology. Developed by the China Precision Machinery Import and Export Corporation, the HQ-9 draws inspiration from the American Patriot missile system. Reports suggest that China acquired the Patriot design through a third-party nation in the 1980s. Like the Patriot, the HQ-9 uses a track-via missile guidance system, which allows it to adjust its course for precise targeting continuously. The missile itself is a 2-stage system. The first stage, with a diameter of 700 millimeters, propels it into its trajectory, while the second stage, measuring 560 millimeters in diameter, guides it toward its target. The missile is 6.8 meters long, weighs almost 2 tons, and is armed with a 180-kilogram warhead. It travels at an extraordinary speed of Mach 4.2, which is 4 times the speed of sound. The HQ-9 can strike targets up to 200 kilometers away and at altitudes as high as 30 kilometers. Its proximity fuse activates when the missile is 5 kilometers from its target, ensuring detonation at an optimal range for maximum impact. The HQ-9 has undergone significant development, leading to various adaptations for different roles. One notable version, the FD-2000, is designed for export and includes anti-stealth capabilities. Another version, the FT-2000, focuses on targeting radar-emitting aircraft, such as reconnaissance planes. The HQ-9 is a naval adaptation for use aboard ships, while the HQ-9A is an upgraded variant that entered service in 2001. The HQ-9B extends the system's range and improves accuracy with a dual seeker. The HQ-9C, still under development, is expected to incorporate active radar homing technology. The missile is launched from a vehicle known as a transporter erector launcher, which is mounted on an 8-wheeled truck chassis. Each TOW carries 4 missile containers that are tilted vertically for launch. Additional supports are deployed at the rear to stabilize the truck during firing. The system also relies on sophisticated radar, such as the HT-233 phased array radar, which can detect targets at a range of 120 kilometers and track them within 90 kilometers. The radar can monitor up to 100 airborne targets and engage more than 50 simultaneously. In its full configuration, an HQ-9 battery includes numerous components. It has a command vehicle, 6 control vehicles, 6 radar vehicles, 48 missile launch vehicles, and nearly 200 missiles. Supporting vehicles for communications, positioning, and power supply ensure seamless operation. The system is designed for efficiency and rapid response, with the ability to defend large areas from multiple aerial threats. The HQ-9 represents a significant milestone in China's defense technology. Its adaptability, range, and precision highlight the country's ability to develop advanced systems that compete on the global stage. With its combination of reliability and innovation, the HQ-9 remains a critical asset for air defense and a key example of China's growing technological expertise. From its inception, the Russian Su-57 stealth fighter caused quite a stir. Its advanced capabilities have raised concerns in other nations, including the United States. As Russia's first 5th-generation stealth aircraft, the Su-57's performance has been compared to the F-22 Raptor, one of the United States' most formidable fighters. But can the Su-57 match or even surpass the capabilities of Western aircraft? In a dogfight, would the Su-57 have the upper hand over the F-22? Or would the American fighter remain dominant? Join us as we explore the insane capabilities of Russia's $273 million stealth jet, which will destroy the West. The Su-57, Russia's advanced 5th-generation stealth fighter, has sparked significant debate since the first day. As the successor to the iconic flanker and a product of over a decade of development, it has drawn mixed reactions. While it represents advanced Russian aviation, some in the West argue it is merely a derivative design. Despite being positioned as the future of the Russian Air Force, only a limited number have been produced, raising questions about its viability. Stealth aircraft became a priority for military powers during the 1980s, with the United States leading the way through the Advanced Tactical Fighter program that ultimately produced the F-22 Raptor. However, misconceptions persist about stealth technology. Contrary to popular belief, stealth does not render an aircraft invisible to radar. Instead, it minimizes detection time, delaying an enemy's ability to achieve a radar lock. This principle underpins the designs of the F-22, an air dominance fighter meant to neutralize threats before adversaries can respond, and the B-2 bomber, built to evade defenses and penetrate deep into enemy territory. With the Su-57, Russia aimed to combine stealth with maneuverability, promising an aircraft capable of countering Western advancements. But is it an underestimated game changer or merely overestimated propaganda? In response to emerging technologies in military aviation, Russia adopted a different approach, prioritizing high performance over stealth. This philosophy led to the launch of their 5th-generation jet program, known as the MFI. The program aimed to develop a competent aircraft with moderate radar cross-section reduction. This effort culminated in the creation of the MiG-1.44, which ultimately failed, showing the broader challenges Russia faced during the 1990s. Despite the MFI program's shortcomings, Sukhoi took the initiative to independently design a next-generation fighter, resulting in the S-37 Berkut. This self-funded project was a technological demonstrator, showcasing advanced capabilities, including its iconic forward-swept wing design. The S-37 symbolized a vision for the future of the Russian Air Force, inspiring further innovation. By the early 2000s, following the MFI's failure, the Russian government launched a new program called the PAK-FA, also known as the Prospective Airborne Complex of Frontline Aviation. Sukhoi and Mikoyan had very different strategies for the PAK-FA competition. Mikoyan suggested a team effort where 3 design bureaus, Mikoyan, Sukhoi, and Yakovlev, would work together, with the winner leading the project. On the other hand, Sukhoi wanted to lead the entire project from the start, including everything from design to production, working closely with suppliers and research teams. Their aircraft designs also showed different priorities. Mikoyan's prototype was smaller and cheaper, weighing 16 to 17 tons and powered by two Klimov VK-10EM engines with about 10 to 11 tons of thrust each. Sukhoi's T-50 was bigger and more powerful, weighing 22 to 23 tons and using two AL-41F1 engines with 14.5 tons of thrust each. In April 2002, Sukhoi won the competition and became the lead designer for Russia's next-generation fighter. The Ministry of Defense chose Sukhoi for its strong proposal and its proven track record in creating Su-27 variants and successful exports during the 1990s. Flight tests were expected to begin in 2007. However, its production has faced numerous delays, highlighting ongoing challenges in fulfilling this ambitious vision. Russia's fifth-generation fighter jet remained secret for years, sparking intense debates on military forums, blogs, and news outlets. However, the veil was lifted in 2010 when the first images and videos of the Su-57, previously known as the T-50, emerged. The footage showcased the aircraft's maiden flight, captivating the media. Critics quickly dismissed it as an imitation of the F-22 Raptor. But the truth lies somewhere in between. The Su-57 stands out as a unique platform with distinct design choices. While its wing shape may resemble American fifth-generation fighters, the resemblance ends there. Unlike the F-22 or F-35, the Su-57 incorporates design elements from the Flanker series, such as engines housed in gondolas and a tunnel structure between them, enhancing lift and maneuverability. The aircraft's canted vertical stabilizers reduce radar visibility, a crucial feature for stealth, and function as control surfaces, a concept reminiscent of the YF-23. This American prototype was lost to the F-22. Interestingly, the Su-57's nose section resembles the YF-23's naval variant concept, the NF-23, more closely than the Raptor. Additionally, the Su-57 integrates horizontal stabilizers and leading-edge root extensions, which act like canards during flight to maximize maneuverability. These design choices highlight its focus on agility and versatility. From its prototype stages onward, the Su-57 has demonstrated a blend of innovation and inspiration, solidifying its position as a distinctive and formidable aircraft. From its inception, the Su-57 has showcased a design philosophy centered on maneuverability and versatility, setting it apart as a unique player in fifth-generation fighter jets. Unlike the advanced stealth coatings of the F-35 and F-22, the Su-57 uses radar-absorbent materials sparingly, focusing on critical areas like hatches or sections prone to radar wave scattering. This limited application reduces the jet's radar cross-section by 20% to 90%, far from the exaggerated claims of massive reductions. While the Su-57 cannot match the stealth of its American counterparts, it's stealthy enough for Russian standards. Modern radars would still struggle to track a target with an RCS below 1 square meter. However, the Su-57's stealth effectiveness is hindered by its exposed engines in the rear, which likely results in a higher RCS compared to the F-35 and F-22. While some media criticize details like exposed screws, these aren't a significant factor, as even the F-35 and F-22 have similar features and maintain exceptional stealth capabilities. The real challenge for the Su-57 lies with its engines. Russia repeated a familiar Cold War mistake by starting the development of the aircraft before designing its intended engines. While other successful jets like the Rafale and Su-27 also began testing with interim engines, they quickly transitioned to their proper power plants. The Su-57, in contrast, still relies on engines not explicitly optimized for its design, limiting its full potential. The story of the Su-57's engine development is long and still unfinished. Currently, the Su-57 jets in production are powered by AL-41F1 engines, which are closely related to those used in the Su-35. While these engines are reliable and robust, they are not the original design and vision for the Su-57. Instead of being based on the AL-41FS developed for the older MFI program, they are adaptations of the older AL-31 engines. This means that unlike some fifth-generation fighters, the Su-57 may not achieve sustained supercruise, flying at supersonic speeds without afterburners when carrying a full combat load. For comparison, even the Su-35 can only achieve supercruise in a lighter configuration. On the bright side, the AL-41F1 engines feature 3D thrust vectoring, giving the Su-57 exceptional agility and maneuverability. The Su-57 is a formidable dogfighter with a thrust-to-weight ratio of over 1, even in combat configurations. However, modern air combat has shifted away from traditional dogfights, making this capability less critical in most scenarios. The future engine for the Su-57, called the Li-30, is expected to bring substantial improvements. It's designed to enable supercruise at speeds up to Mach 1.5, incorporate serrated nozzles like the F-35's F-135 engine, and potentially introduce a flatter, stealthier nozzle design inspired by the S-70 Okhotnik drone. These upgrades aim to improve stealth and reduce the visible titanium areas affecting the Su-57's radar signature. However, it's unclear when these new engines will enter service. One of the Su-57's most promising developments is its collaboration with advanced drones like the S-70 Okhotnik. This wingman drone is far more focused on stealth, with a sleek design and large payload capacity. Working alongside the Su-57, these drones could change the dynamics of air combat. For instance, the Su-57 or an AWACS aircraft could identify enemy targets, while the S-70 drones engage them undetected. This teamwork could make the Su-57 and its drones a powerful offensive or defensive force. Russia is developing a new data link system called OZOD, similar to NATO's Link 16, to support this integration. This system would enable seamless communication between manned aircraft and drones, enhancing operational efficiency. The S-70 has undergone several successful test flights and continues to advance through its development phase, promising a significant leap in Russia's air combat capabilities. The Su-57, Russia's advanced fifth-generation fighter jet, is more than just a concept. It's a tangible project with prototypes in limited operational use. However, the ongoing war in Ukraine and the strain on Russia's military resources raise a critical question. Where will the funding come from to support such ambitious and costly projects? Initially, India partnered with Russia in 2007 to co-finance the Su-57's development under the PAC-FA program. In exchange, India would receive a two-seater variant and the rights to produce the aircraft domestically. However, the program faced significant setbacks, including delays caused by engine development challenges and the integration of entirely new avionics, radar systems, and sensors. Frustrated by these delays, India withdrew from the project in 2018. It retained the option to purchase the finished aircraft later, if it ever reached mass production and full operational capability within the Russian Air Force. Russia initially planned to produce 200 Su-57s, but drastically scaled back the goal to a single squadron of 12 aircraft. This number was later adjusted when, in 2017, a contract for 76 units was signed. Despite this, progress has been slow. To date, only around 10 Su-57s are reportedly in operational service. The Su-57 has allegedly been used for testing in Syria and even deployed in the war in Ukraine. Reports suggest it may have engaged in air-to-air combat, with claims of a possible kill against a Ukrainian Su-27. However, these claims remain unverified and fall into the realm of speculation. Funding, production delays, and operational challenges continue to overshadow the Su-57's development, raising doubts about the project's future viability amidst Russia's current economic and military constraints. This conflict has been as much about propaganda as it has been about military advancements, creating the impression that the Su-57 is a game-changing aircraft in combat is a powerful tool for Russia to appeal to potential buyers worldwide. However, it's crucial to approach such claims with caution and a critical mindset. Now, addressing the big question, how would the Su-57 fare against America's finest? The F-22 Raptor or the F-35 Lightning II? Let's delve into its capabilities, focusing on its electronics and weaponry. The Su-57 is equipped with the advanced NO-36 Belka AESA radar system, which consists of 5 distinct antennas. The primary X-band antenna provides long-range detection and target engagement capabilities. 2 additional X-band antennas on the sides enhance coverage, extending to approximately 270 degrees. Furthermore, two L-band antennas integrated into the wings support electronic warfare functions, broadening its defensive capabilities. At the front of the aircraft, there's the infrared search and track system. This system can detect thermal signatures from enemy aircraft and guide infrared missiles without needing the radar. It is similar to the electro-optical targeting system on the F-35. Notably, this is an advantage over the F-22 Raptor, which lacks a comparable IRS system, though future upgrades might address this gap. The Su-57 also incorporates sensor fusion, where its onboard computer integrates data from multiple sensors to improve the pilot's situational awareness. While this is a step forward, it doesn't match the advanced capabilities of the F-35 distributed aperture system and the helmet-mounted display, which offer unparalleled situational awareness and targeting accuracy. One notable drawback of the Su-57 is the absence of an integrated targeting pod, unlike the F-35. The F-35 can engage ground targets using its internal systems while maintaining its stealth profile, a significant advantage in modern combat scenarios. So to conclude the comparison, the Su-57 is a formidable aircraft with features that outpace fourth-generation and even advanced fourth-plus generation fighters. However, in a head-to-head comparison with the F-22 or F-35, it falls short in several key areas, particularly stealth and electronic warfare systems. While impressive in its own right, it remains a step behind its Western counterparts. The Su-57 is undoubtedly a remarkable fighter, but what lies ahead for this program? While the Su-57 isn't flawless, it does showcase strong capabilities. It features advanced radar and avionics, respectable stealth attributes, and powerful engines, though these engines have yet to meet the originally planned specifications. The anticipated Su-57M upgrade is expected to include these improvements, along with advanced systems. However, futuristic elements like autonomous drones remain largely conceptual for now. In combat scenarios, the Su-57 poses a significant challenge. Equipped with R-37M long-range missiles capable of striking targets over 200 kilometers away, it could potentially engage adversaries like the F-22 and F-35 before being detected. Russia envisions the Su-57 as a command aircraft, leading jet teams to enhance battlefield surveillance and support. However, the program faces substantial hurdles. Current production numbers are low, with only 10 to 15 operational Su-57s and an order for 76 more. Even with these, the fleet falls short of matching the U.S. F-22 inventory and the extensive fleet of over 1,000 F-35s deployed by the U.S. and NATO forces. Interestingly, while debates often pit the Su-57 against Western fighters, the Chinese J-20 may represent a more immediate concern for the U.S. With its serial production and growing numbers, the J-20 could more effectively challenge the balance of power than the Su-57. The J-20 stealth fighter is designed to dominate the skies with cutting-edge technology. Its advanced sensors and data systems give the pilot a complete view of the battlefield while using stealth and electronic warfare to keep enemies in the dark. The aircraft has a suite of sensors that provide a 360-degree view, and its nose-mounted systems are tailored for detecting and engaging air threats. Though exact details about its radar remain secret, experts believe the J-20 uses a high-performance AESA radar capable of tracking targets up to 200 kilometers away and engaging multiple enemies simultaneously. It also includes electro-optical targeting systems and infrared sensors, similar to those on the F-35, making it especially effective against stealthy opponents. Pilots enjoy a fully digital setup inside the cockpit with a massive touchscreen display, additional auxiliary screens, and a wide-angle holographic HUD for critical data. The helmet-mounted display lets pilots aim and fire weapons by looking at the target, even at extreme angles. Recent reports suggest the J-20 is also capable of airborne early warning and control, further boosting its versatility. With all these features, the J-20 blends stealth, precision, and cutting-edge avionics into one formidable package. The J-20 fighter jet is designed to carry advanced weapons for various missions. Its primary weapons bay can hold long-range air-to-air missiles like the PL-15 and PL-21, as well as precision-guided bombs such as the LS-6 series. Two smaller side bays near the air intakes are made for short-range missiles like the PL-10. These side bays are built for stealth, letting the doors close quickly before firing, making launches faster and harder to detect. The central bay can fit up to 4 long-range missiles, while the side bays each hold 1 short-range missile. By 2023, reports suggested China was working to boost the J-20's missile capacity. A new staggered setup could allow 6 PL-15 missiles to fit internally, and a slimmer missile called the PL-16, designed with folded fins and a compact frame, is also in development. Despite its smaller size, the PL-16 matches the PL-15 in performance. The J-20's primary mission is air combat, using missiles to take down enemy aircraft and critical aerial targets. It might also handle precision strikes with air-to-ground weapons or anti-radiation missiles. While its wings can carry extra fuel tanks or larger weapons like the PL-17, this would reduce its stealth, so it's not the jet's primary role. Interestingly, the J-20 doesn't have an internal cannon, hinting at its focus on long-range battles rather than close dogfights. Its design prioritizes precision and power when hitting targets from afar. The J-20 stealth fighter is designed with a brilliant mix of features to reduce its radar visibility. Its shape uses canard wings paired with smooth extensions near the leading edges to scatter radar waves effectively. The sleek forebody, radar-friendly canopy, and specialized materials help it achieve stealth like the F-22. Its air inlets, called DSI, are cleverly designed to hide the engine from radar, while also being lightweight and simple. The J-20's weapons bay has flat bottoms, doors have jagged edges, and cooling vents have mesh covers to improve stealth further. While some argue that using canards could hurt its stealth, experts point out that canards can work with low observable designs, as seen in other stealth aircraft. Advanced flight controls and careful engineering make them viable for stealth. The aircraft also uses composite materials and radar-absorbing paint. During peacetime, a special reflector makes it visible to other planes, enhancing safety and reducing training risks. This reflector can be removed in combat. Over time, the J-20 has evolved to include better engines and stealth-enhancing features, especially in its newer models. While its rear stealth isn't as advanced as the F-35, its front-facing stealth is impressive and better than the Su-57. Analysts believe the J-20 can use its stealth to strike targets in cluttered airspaces, showing it's a serious player in modern air combat. In a nutshell, the J-20 is formidable. The future of the Su-57 is uncertain, especially given the pressures on Russia's defense industry due to the ongoing conflict in Ukraine. Nonetheless, its design and the F-22 will likely influence the development of next-generation fighter aircraft for years to come. Despite criticisms, the Su-57 remains an impressive platform, hinting at the potential change of the future of aerial warfare. Thanks for watching. While you are still here, click on the link on your screen to check out another of our videos. See you there.